A little bit about the grading in this class, because we are doing most of the lectures, actually all of them, at least at the moment, this is the plan. We are doing everything online. The final grade will be composed from 30% or 3 points that are coming from exercise sessions, 4 points or 40% that are coming from home assignments. So it will be 4 home assignments that will be provided to you after the lectures, and you are invited to send solutions. And 3 points or 30% that are corresponding to the exam, and the exam will happen at the end of the semester, and will be an extra bonus point of 1 point or 10% that's coming from attending the lectures. Optionally, we are planning projects, but those are just optional. So if you are interested in projects, then you can do such a project individually or in group. And the grade in that project, how well you are doing in that project, will be used either to improve your final grade or to replace the exam grade. So if you're doing very well in the project, then it's very likely that you can just replace the exam grade with the grade in the project.
If we are to replace the exam grade, we do not have to sustain the exam anymore, right?
No, exam is mandatory regardless. So if you know that you did perfect in your project, okay, then yeah, you can rely on that. But the exam is still mandatory. You can just come and give me an empty sheet, but it's mandatory. It's just a matter of you, if you want to write down in the exam or not, but it's still mandatory.
The exams are online or in a physical format?
So the exam will be also online, like everything in this class. So will be online examination. The plan is to be somewhere on 11th of June, 2 hours. You'll get a sheet with 8 topics, 8 tasks, plus eventually some bonus tasks. And yeah, you'll have 2 hours to solve them, write them on the paper or whatever is the sport you want. And at the end of those 2 hours, you need to send some photocopies or the PDF or the doc, whatever is the format you wrote the solutions to the exercises. So yeah, it will just be a normal online examination, and you'll just need to video stream on Zoom like now, but you'll need to turn on your camera just for me and the others to know that you are there and doing the exam. And the exam will be in the same, let's say, pretty much similar conditions like when you are doing your home assignments. So you have access to the internet, you have access to the lectures, to the sport, to the materials in this class. And yeah, you can just use all of those to solve your exercises. So I cannot control whatever is the material you are using, but what I can control is the exercise, the problem that you need to solve, and I can guarantee you that you'll not find directly an answer just by Google search.
What is the minimum requirement to pass the classes, the course?
So in our system, or in the system at the Romanian educational system and so on, typically we have 100% or 10 is the maximum grade, and in order to pass you need 50% or 5 points in this class. Okay, so it's just the typical. You just need 5 points out of 10.
Okay, thank you.
Welcome. Okay, are there some other questions? Okay, so you'll find also on the webpage of the class this information. If you have some other questions, you can also ask there on the forum or on Discord, depending on your study program. And yeah, if you don't get answers there, just drop me an email or ask me in the next lecture. Okay, so this is a little bit of organization, logistics. So for today, we have 6 hours of lectures. And yeah, we hope to cover some 4 or 5 topics. And yeah, probably the best is to take some breaks after around 40 or depending 1 hour and something of a lecture. We'll take some 10-15 minutes of break and we'll repeat this until the end of these 6 hours. Or yeah, depends if the material that I'm covering, or if we are going faster, we may end the lecture session sooner. Okay, but this is a matter also of agreement with you. Maybe you prefer to take the breaks instead of listening to a long lecture. Okay, so let's start the first lecture with computer vision. So why vision? It is a crucial characteristic, is a crucial feature, is a crucial function that we as humans we have, and not only us. So why vision is important? Half of our brain is devoted to vision. Okay, depending on the studies, some might say that is more or less, but roughly a big chunk of the brain is devoted to vision. Vision developed many times during evolution. So vision is a non-contact sense that we have, and vision can be implemented with high resolution. So if we are thinking about our eyes and our vision system, we are getting quite detailed information about the surroundings. Then vision is working with ambient electromagnetic waves, so we don't need some extra active sources for support or for providing us the vision. And the vision is giving us color, texture, depth, motion, shape, this kind of information about the surroundings. So in the end, vision is helping us as individuals, and not only us, many other living beings, animals, organisms, to interact and to perceive the surroundings and the other beings. So is a essential sense, and for a right reason. Okay, so for people, vision is their most crucial sense, and it is for a good reason. It is placing us in the context. Obviously, we have some exceptions, like the blind people, and they are compensating through the other senses. Okay, why vision? It is very intriguing. So if it's to look at this image, the perception of intensity is different, depends on the context. So here we are having two columns of gray levels. So probably all of you will just consider that these two columns or these two gray columns are having somehow different levels of gray. Well, this is wrong. On the color level is the same. The gray level is the same. What is different is the context. And because of this context, we are just deceived. Perception of color is changed or wrongly changed into thinking that we have different gray levels here. So we need to pay attention at what our eyes are telling us, what our perception is telling us. So another example here, we have the perception of color. And in this example, we have some red squares and some green squares. Well, because of the positioning and the immediate surroundings, we have the green squares on this diagonal. Again, most of you probably you'll see somehow different levels of red for these two diagonals. Okay, so the context plays a key role in deceiving or in creating the perception in our brain, the perception of color, the perception of what happens in the surroundings. So here is another example, the perception of length again. So if we are looking in case A, B, or C, the immediate direct feeling or what our eyes are telling us is that these two horizontal lines or segments here, in each case, or here, those that are not marked but are ending in these arrows, they are of different lengths. Okay, so at least for eyes, for our eyes, typically is quite likely to tell us that these lengths are different. And this is based on the end points of these segments. And because of our priors, what our vision system, our brain was used to work with and gain from experience, then is projecting on this particular case and is telling us that might be different or are different. However, actually these segments are of equal length, and the endings are the ones that are changing our perception of length for these segments. So here are some other examples about how our brain is interpreting straight lines in the context. So for example, here on the top left, we have a vanishing point and for a set of lines and two parallel lines. However, because of this vanishing point and set of lines that we have here, our brain starts to see that these parallel lines are bending, so are curving. And well, we know that this is not the case, but our perception, our brain, is telling us anyway this. This is our interpretation of the world, even if the world is not like that. Here we have a set of circles, and overlaid we have a square. Because of these circles, our brain, our visual system, is telling us that the edges of this square are somehow curved, but actually it's not the reality. Also, if we are looking at this checkerboard, because of these small dots that are placed on the black squares, the black patches here, we are deceived into believing that somehow the lines are bending in the middle part of the checkerboard. Well, again, this is just a wrong interpretation of what really happens in this image. And yeah, already I'm just pointing out that our brain takes the context into consideration, imposes quite a number of priors, and our interpretation or what we believe might not be the true. So our vision system is deceiving us into believing something that is not necessarily there. Here are some other examples. Because of the placement of the black patches, we are believing that these lines here actually are not parallel. Somehow they are supposed to be tilted to some, with some angle to the left, to the right. Okay. But it's not the case. The same here, because of this, we can just think that the lines again are not parallel, or are parallel only those that are carrying the same pattern. But yeah, actually the lines are parallel here, and because of the pattern, we our vision system is just interpreting wrongfully what is there. So this is another example. Because the placement of these arrows, we are starting to believe that this top part is not really parallel with the bottom, but actually is parallel. Okay, so are plenty of such examples that are showing that our perception is deceived, or our visual system is giving us the wrong information about the surroundings. So I won't enter in all these examples listed here. This is a very interesting example of perception of intensity. I don't know about you, but in my case, here is almost difficult to focus my eyes on, because the brightness of this area seems to be very high. But the reality is that what is here, the level or the whiteness of this patch here, is at the same level like the one on the left side. But this perception of intensity or brightness in our eyes, in our brain, and so on, is influenced by the surroundings. And if here we have just black patches, on the right side we have a gradient placed on these patches, and this gradient is making our brain to believe that actually the brightness is continuously increasing, and we are getting over bright region in the middle. So this is another case that is quite strange, because also our eyes are just getting fatigued just by looking to this area. Okay. So another typical deceiving effect, or how to call it, illusion that our visual is creating for us, or our brain is creating for us to interpret whatever eyes are seeing, is shown here. So if we are getting some small pieces, everybody probably can read the read word. Okay. Also, if we are looking at these end points, almost everybody will start to think that they are marking the points of a triangle. The more such helping or contextual cues, the more likely our brain will start to fill the missing pieces. So here, one might consider that we have a triangle here, and we can also think that we have another triangle that actually is in the continuation of these corners here. So what I discussed so far is showing that there are quite a number of cases where our vision system and our brain is interpreting wrongfully the surroundings. But at the same time, part of the reason of why we are doing this is also are about the same reasons that in the end are helping us to handle the context or the surroundings. So basically, the illusion effect and imposing some priors and starting to believe that if we have something here that is placed, we'll just make this upper part to be slightly tilted, okay, is the kind of prior that is helping us to navigate surroundings on a daily basis and is helping us to fit patterns in the surroundings. So without this interpretation that if we have some gradient, we'll just continue and get some extreme point at the end of that gradient, okay, then we as humans, we might end up looking or staring to the sun quite often. And this is might harm our eyes. Or without, for example, getting back here and without interpreting this kind of cues that are in the end contextual, okay, we may not, when it's the case of really finding some patterns in the surroundings, we may not properly interpret that kind of natural patterns that are appearing. So in the end, in most of the cases, when we are interacting with the surroundings, having this kind of endpoints or patterns, in most of the cases, is also likely that actually this delineates or denotes different segments or different lengths of segments. Okay, so it's the kind of priors that we are learning in our life and is helping us to navigate and is helping us to create or imagine or hallucinate patterns in the surrounding world. Okay, so if we are seeing this kind of endings, already we are fitting a pattern, and fitting this pattern already is helping us to do something or to react. So if we are seeing some occluded traffic sign or some other occluded people, or okay, already we are fitting a pattern and we are seeing that it's supposed to be a traffic sign or it's supposed to be a person, okay, and we are already take some actions that are helping us. The same is coming with the reading. So if we are seeing some edges, already we are fitting some pattern and we are reading beyond what is written there. And this helps us to cope with noise and to cope with whatever deformations of the writing, especially the handwritten text. Okay, so if we are looking at this picture, probably after looking for some seconds, most of you will just interpret that here must be some dog, when actually the picture is just a black and white picture and is not necessarily containing a dog. So we are continuously projecting our priors in the images and what we are seeing with our eyes. And the role of context is very, very important. So here we have 4 scenes or 4 images. And if it's to mark, we have these regions marked with red circles. And in all those circles, we are seeing a pattern, okay, that is coming at different angles. But nevertheless, it's about the same pattern that we are seeing in all those images. What differs is the context. If we are at this level of resolution, so it's a smoothed image, these patterns are looking about the same. In order to differentiate or to interpret what is the real nature or to identify what is that pattern, we need to look at the context. So if we are getting this context and we have our pattern, so probably most of you will just consider, okay, here is supposed to be some building, we have some street, we have some pattern. It's very likely that this pattern is a pedestrian that is sitting on the side of the street or on the street. Okay, but if we are changing the angle and we are placing horizontally, then already we are starting to think, okay, it's supposed to be a car, especially if it's placed in the right position. Okay, so I'm pointing out here that our human vision is much more than a bottom-up process of subsequent signal processing steps. So what means this? We are not simply taking local decisions in the image and then we are just placing them together. We just need to go both top-down and bottom-up in order to make some sense about what happens in an image. Okay, so the effective vision needs more than sheer filtering and measuring. So it's not sufficient to identify a pattern in order to assign a meaning to that pattern. We need also some context and some extra cues. Okay, another reason why we are interested in vision, and especially in computer vision, it is a very hot topic. So this is a plot, it's already a bit outdated. Now we have quite an exponential curve here, and it's much more impressive. Okay, so it's showing the number of photos per year captured worldwide. And we can see here that the analog photos are facing a major decline, while the digital photos are dominating in the photography and in the whole mass of such photographies. So this is because of the mobile devices, the smartphones. Now everybody has a smartphone, and typically a smartphone comes with a camera, and everybody can take easily a large number of pictures and also is sharing on internet or is storing on their personal computers. So now capturing photos or getting videos is easier than ever and the cost to do this is very low. Also, the storing of such images and videos is quite cheap. And yeah, the direct consequence is that nowadays most of the photography is coming from mobile phones, and we have huge amount of such photographies and video recordings. At the same time, if we are looking at what means computer vision, by the way, computer vision in the end is aiming at understanding what happens in a visual data. Visual data may be RGB, so 3-channel image, like the common photographies or images that you are working with, or could be videos, movies, or sequences of images. So the computer vision is aiming at understanding what happens in such images, at the same time at representing and interpreting what is there, and at manipulating such visual contents. So, and the aim of computer vision is, in the end, to do almost everything that a human can do with its own vision. So if a human can interpret, organize, analyze, manipulate some visual contents, then the computer vision is supposed to be able to come with algorithms or solutions that are running on computers that are doing the same thing. So we have human vision and we have computer vision. So if for human vision, we have the brain and we have our visual cortex and everything to help us, for a computer, we need to design solutions, algorithms, and this algorithm will just give to the computers the capability to solve tasks that are typically seen in the human vision. So if is to look at the field of computer vision, in the early, let's say 50 years ago, 30 years ago, most of early applications or algorithms of computer vision were found and designed in production environments, and these were pretty much constrained and were working on for controlled conditions and were having little uncertainty on the visual data they were working with. So, and you can just imagine what means such controlled environments. Will be some assembling line where we have always some reduced number of pieces that are supposed to be placed together, and these pieces are well known, their geometry and so on, or we are in a medical environment and so on. Okay, but currently, actually, computer vision applications are everywhere. We are handling and we are aiming at everything that means real world applications, real life. So we are aiming at direct, let's say, visual data streaming, for example, that is coming from surveillance, from recordings, from social or conferencing, video conferencing, or remote sensing from satellites or medical settings, and so on. And yeah, at the moment, we are seeing a lot of applications that are reaching the point of being usable and replacing or augmenting what humans are capable to do with visual data. Here are quite a number of examples just to give you some feeling about what are these application areas. So, for example, here are two images. One at the top is an image that is captured by a smartphone. If we are looking at a smartphone, the smartphone has a small camera. The small camera has a very small sensor that is capturing the image. And because of this physical constraint, typically the quality of the images that are captured with smartphone cameras is quite poor in comparison with the DSLR or professional cameras or dedicated cameras that may have larger sensors and some extra stabilizers that can capture much better what happens in a scene. Okay, and then obviously one might want to get the quality of the expensive professional camera for his own smartphone camera. So in a different way of saying, you want to get pictures of the high quality, expensive professional camera with your low quality, small sensor, camera sensor from your smartphone. So this is one example of application that is mapping the images from the camera sensor that is found on a mobile device, smartphone, to a high quality space that typically is found on expensive professional cameras. So this is an example of image enhancement or quality enhancement of images. Okay, another example, and probably everybody already noticed that there are all kinds of tools that are allowing you to generate, to synthesize faces. And it's not only that you can see synthesized faces, but those faces actually are different than any human or faces on Earth. So basically are new constructed faces, and these new constructed faces, actually they are not representing people, are just faces from the same domain of faces, okay, so are purely synthetic, and you can just generate infinite amount of such faces. So this is a task of synthetic generation of samples in a given distribution. So the distribution in this case is the, let's say, set of face images that is coming, let's say, from known sources, so are real face images. And then the task is to model this visual data, this distribution, and to be able to sample new face images in that distribution. And these new sampled face images, like those 8 here, are completely new. So are new identities, new faces, unseen, unreal, are not from the real world. Okay, so this is another task and application that we are very successful, and we can generate in a very high resolution such faces. Okay, so for the past more than 10-15 years, probably you notice the autonomous vehicles story was huge hype, still is. Okay, and the final aim is to have self-driving cars to replace the driver, the human driver, with the onboard computer that is taking the decisions and is able to drive the car as a human could do it. Okay, and in order to have self-driving cars or autonomous vehicles, obviously we need to be able to uh, uh, provide some solutions or algorithms that are capable to do everything a driver could. So if the driver is having a number of inputs, and those inputs are mainly visual, but also some other readings on board, readings from the car and so on, and also the self-driving application or the solution that is driving the car is supposed to be able to do the same. So it's supposed to interpret the visual input, it's supposed to interpret the readings about the status of the car, it's supposed to interpret the interaction in the traffic. So all of those, we need solutions, algorithms that are running on computers or GPUs or CPUs. And the final aim of those algorithms is to create some models and predictive models that in the end are helping to take decisions, and everything, the decisions and the prediction and the driving is supposed to happen in real time. Okay, so here is just some simple depiction of some, car or some more expensive car, Lexus and so on. And here are some depictions of the car in some surroundings. And we can have a LiDAR or readings that are giving us some information about the distance, or directly we can have some stereo cameras that are giving us some information about the distance. The objects are from the stereo cameras, or we can have just monocular vision. This means that we have only a single camera and is looking ahead. Okay, but yeah, each self-driving car or autonomous vehicle system will have a number of inputs or sensors and a specific solution that is maximizing the benefit of using those sensors. And yeah, probably you are quite aware about Tesla cars, and Elon Musk is one of the few in industry that is considering that the autonomous vehicles are supposed to be able to function only by using the visual information, because the humans are capable to do that. But yeah, other people and other companies are considering that it's better to augment and to add some other sensors in some other domains. Like, yeah, you can imagine you can have infrared, so going beyond the visible spectrum, the humans are seeing just like you and I, the reduced spectrum of the color space or color spectrum. Okay, while they are there thermic or thermal images, near infrared images, you can have also some readings about distance like LiDAR and so on. And this kind of information can be quite helpful, especially in the traffic and to control what the car is doing. Okay, so in order to have autonomous vehicles, we need to interpret everything that happens in the traffic. So it's not sufficient just to have an idea of what happens in the context, in the surroundings, but we need to identify, track, keep the track, and do or cast predictions for everything that happens in the surroundings of a car. And we need also to track the lanes, just to keep the car on the right side of the street. Okay, And yeah, all those representations and interpretations and forecasting will help in the end at making decisions about the car, where to turn the car, how to move the car, what speed the car to have, and so on. So, as mentioned before, we can have multiple modalities. It's not only the visible spectrum, we can go in some invisible spectrum, we can have all kinds of readings, and we can have a 3D reconstruction of the surroundings. And everything is supposed to be combined or placed together in order to get the best, the most reliable self-driving car solution. So here is just a simple bird view or top-down projection about what some mobile platform is looking at. So here will be like the mobile platform, and here are some rays and are showing some objects that are occluding. Okay, the view of the mobile platform. Okay, and some estimates like depth to the nearest object, to the farthest object, and so on. Okay, so some other vision applications are very interesting and quite common nowadays. If you are looking at Facebook, and not only, if you have slow connection or the images or the videos are not loading, typically you'll get some textual description about what is in that image or in that video. So this textual description is, or in the computer vision literature, is also named captioning, image captioning, video captioning, and so on. So we are aiming at getting a textual description of the visual content. So here are some examples. On the first column, we have some images and we have some automatically generated description. And this automatically generated description is matching quite well what is in the image. And yeah, the more we are going to the right, we are seeing how this image captioning solution starts to have problems. Okay, so by now you know very well that typically the solutions in the real world are not perfect and they can have errors. And the solutions or the final aim of the research and so on is to reach 100% accurate solutions and to remove as much as possible those wrong predictions or results of the solutions. Okay, so this is very helpful. We can just get a textual description. This textual description in the end means that we have actually an understanding of what is in the image. So here we have a group of young people playing a game of frisbee. In order to generate this caption, we need to understand that we have people, that they are young, that they are exhibiting some interaction, so they are playing, and we have a frisbee there, and in this way we can say that it is a game of frisbee and is not some other game they are playing. Obviously, this caption is not perfect. A full description here will contain something about the ground, okay, the grass that is on the ground, something about the trees in the back, the houses, and do even more further refining the contents. Okay, but yeah, a very short captioning is saying just the essential part, and this a group of young people playing a game of frisbee is pretty much the main thing that happens in that picture. So the same goes for example in here. We have a person riding a motorcycle on a dirt road. Okay, so is the basic description and is the main description there. But in the reality, we already can see that there is a second person here. And we, with our vision and our priors, we are understanding that it's supposed to be a third person here because already we are seeing some wheel. And this is supposed to come from a motorcycle, and the motorcycle doesn't ride by itself, at least not nowadays. Okay. So it's supposed to be like three persons here. And then it's not a dirt road. If it's to further interpret, is pretty much a race, and there are three that are racing, and we have some numbers that are placed in some meaningful position, and we can even say the numbers of the participants in this race. Okay, so our vision and our understanding and so on can be more complex than what a computer algorithm or solution can do. But yeah, are still plenty of things that we can do and improve. So other applications of vision are in surveillance. And here are just a couple of examples, just surveilling around some residential place, and you are looking for trespassing, or you are surveilling the traffic on some main boulevard or avenue in a city, okay, and you are tracking the cars and get statistics. Okay, and already you have seen this in many football and not only transmissions. Okay, we have augmented reality. We have some, let's say, some broadcasted sport event like football or baseball or whatever. Okay, and we are seeing overlaid all kinds of advertisements, or we are seeing overlaid all kinds of statistics or distances, or we are seeing some path that a player followed and so on. So this is the kind of solutions, computer vision solutions, that are giving us extra information, or is just interpreting what happens in the stream, in the video stream, and we can just provide extra understanding or manipulations of this video stream in some directions, either giving to the audience, feeding the audience with some advertisements, like placing here some advertisement where it was none in the original stream, okay, or Coca-Cola where it was none, or delivering some analysis, some information, and making the audience aware of that information. Okay. And yeah, many of you, okay, all of you probably watched recent movies, and you saw the the kind of generated characters that are there. In order to have this kind of high quality generated characters in a video, in movies, behind we have quite a number of techniques, and these techniques are helping on one side to capture what a real actor is doing to personate or impersonate a character. Okay? And then on top of understanding what that real actor is doing, we are generating, and the generation is supposed to be the part of computer graphics, okay? But also computer graphics and computer vision are going hand in hand at some point. If computer vision is understanding, interpreting, and representation, the computer graphics is going more into rendering realistic or photorealistic vision or visual graphics, visual data. Okay, so here are just a couple of examples. We have the Sméagol, we have the Avatar, we have here some probably Polar Express with Tom Hanks, okay? And in all those cases, the reality is on the left, and what we are seeing is on the right in the movie. Actually, here we just have like a intermediate result that is showing a skeleton or a model of the body of the actor. Okay. So other application domains for computer vision are computer-assisted surgery. So nowadays, non-invasive surgery or laparoscopic surgery is quite common, but also there are a number of applications for remote surgery or just standard surgery that is helped, or like here, computer assisted. And in the sense of the surgeon is placing the tools and so on in the cavity, in the human cavity, has some small sensors. We are capturing some data, visual data, and this visual data needs to be interpreted. So we need to segment, track, analyze, and provide a feedback about what happens there. And this provided feedback is overlaid and provided to the surgeon, eventually in real time, and to help the surgeon to take decisions on the whatever is the activity thing. Okay. Another application is mobile mapping. And for mobile mapping, yeah, already you know the Google Maps, and not only. So simply said, there are some cars with all kinds of sensors that are moving through the cities and are just capturing and creating in the back are created 3D models of the streets and everything that is there, like street furniture, and not only. Okay, so what is a take-home message here? Nowadays, it is feasible to let most things see and interpret their environment. Those things are not only humans, are not only huge computers, but are just small devices that are having some processing unit. And already, if you have a processing unit and you can run an algorithm, you can have a smart solution that is interpreting some data and is providing some information that is adding some smartness to those devices. Okay. Well, in order to have vision, we need light. Without light, we don't have electromagnetic waves. We don't have electromagnetic waves, we are seeing nothing. Okay, but about light, probably we'll discuss in, let's say, 12 minutes. So let's take a short break before. Okay, so let's get back in 12 minutes. So this means at 20 past 10, and continue with the what means light. Meanwhile, I'll be here. So if you have questions, just let me know. You can write them in the chat or just unmute yourself and let me know. Okay. So, do you have questions? If no questions, then let's proceed with light. Okay, so we need light in order to have vision. Simply because the vision is based on electromagnetic waves. Basically, is based on the interaction of some light sources, some light from some sources, light sources, okay, with the everything that is in the environment. And this interaction is what we are perceiving with our eyes or with our sensors. So, typically, in an interpretation system or a vision system, we have a light source, for example, the sun. We have a surface. This could be the ground or some scene, okay, that is reflecting part of this light that is coming from the source. And then we have a sensor or a camera that is sensitive to the reflected light by the surroundings. Okay, so we'll see a little bit more about what means camera, maybe in half an hour or so. Let's first focus on what means the light and the light source and what means interaction with the surroundings. Okay, so the nature of the light and the interaction with the matter. First, and the more important, what is a light? The light is an electromagnetic wave. So this means that as a duality, we have electric and magnetic interpretation of this. Here's just a simple description of the wave and the main characteristics. So we have the wave, the wavelength defined. Okay, so first thing first, those are basic information about electromagnetic waves. Here is just a summary of what means electromagnetic wave and the main characteristics like wavelength and what represents the wavelength, the amplitude, what means a phase, and what is the electric component and magnetic component, the fields, and the direction of polarization. So we have a direction of propagation. So the wave is coming from some source and is going or is received by some sensor. Okay, and we have a direction that's coming from a source and goes to some target. Okay, we have a phase for that wave. We have a wavelength. We have some amplitude of the wave. Okay, and we have also a direction of polarization. So this means along the direction of propagation is like another direction in the space that is showing a tilting of the wave. Okay, so when it's coming to the wavelengths and the electromagnetic spectrum, typically we know or we are exposed and we are working with mainly with the visible spectrum. And this visible spectrum is somewhere between 400 and 700 something nanometers in wavelength of the electromagnetic waves. Okay, and if is to look on the broad spectrum of electromagnetic waves, we have lower wavelengths and we have higher wavelengths. Okay, here, well, this picture was using feet, and that's why is FT there. Okay, feet is the British imperial measure. You know what is approximately 30 centimeters. And here on the lower side, we have the ultraviolet, the X-ray, and gamma rays. So this means that the wavelengths in nanometers are much lower than the wavelengths from the visible spectrum that our eyes are sensitive to. And on the other side, the higher wavelengths, we have infrared, microwaves, TV, and radio. Okay, so visible spectrum from 400 to 700 something nanometers, from blue to red, and then we have ultraviolets on the left side, X-rays and gamma rays, and on the other side we have infrared, microwaves, TV, radio wavelengths, and the radio wavelengths. So this is the spectrum, electromagnetic spectrum, and the common division of wavelengths. And yeah, typically we are working with visible spectrum. Okay, so a common knowledge is that we don't have actually a white or a black as colors or wavelengths. White means basically a combination of multiple wavelengths, while black is just an impression, means that is missing the electromagnetic waves in the visible spectrum and we cannot perceive anything. Okay, so white means combination of colors in the end, and black means absence. And for example, if we are using an optical prism, then we could separate the wavelengths in a white color source, and we can see these wavelengths and generate the visible set of wavelengths, the colors that are going from the boundary to infrared to the boundary to ultraviolet. Okay, so the visible range of wavelengths is somewhere between 380 and 760 nanometers, and conventionally we are giving some names from violet, blue, green, yellow, orange, red to these colors. This is our convention, and as we as humans, we are supposed to be equipped with comparable or the same sensors, eye sensors, and the same brain to interpret. Yeah, we are having these conventions, and typically we are seeing the things in a similar manner. Okay, however, if we as humans, we have our sensors, and typically these sensors are comparable, the cameras may have different spectral sensitivities. This means that the sensors may react or be more sensitive to different wavelengths. And these sensitivities might be different from one camera, from some hardware to some other hardware. And obviously, those will be also different than the human sensitivity. Okay, so we are looking at the visible range. And for example, here we are showing for humans. For humans, we are sensitive mainly around these 3 peaks, around 424, 530, and 560 nanometers. So we have 3 peaks in the visible spectrum. And those 3 peaks are corresponding to 3 types of photosensitive cells that we have in our retina, in our eyes. Okay, so we have such 3 cone types that are sensitive to the wavelengths between 380, 350, and 760. Okay, and those are giving us some perception about what happens in this visible range. We are getting 3 readings that are peaking around these wavelengths that are depicted here. And with these readings that are coming from multiple cells, okay, we are getting a combination, and we are getting a feeling about what is supposed to be the color there. So basically, we are getting a cell that is reading somewhere in, let's say, blue range of colors. Another one that is sensitive somewhere in the green, and another one that is sensitive, let's say, more to the red. Okay, and having these basic sensitivities, then our brain is just making sense out of it and is interpreting combinations, and we are getting an interpretation about the wavelengths that are also in between these peaks of sensitivity that we have in our cells. Okay, and the more such cells we have on our retina, the more the higher resolution our eyes has, so we can distinguish more details. Okay, and yeah, so here is what the human can do, and in comparison we are showing also for a bee and for a bird. What is interesting is that the bees are having 3 peaks that are quite well separated, and the bees are seeing more into the ultraviolet domain than the humans. And this is obviously an adaptation, because the bees probably need the ultraviolet to analyze the flowers and the surroundings. Okay, but yeah, the bees are still having 3 such cone types and 3 major sensitivity peaks, while the birds are not only better in the ultraviolet domain, but a little bit slightly better in the infrared domain. Okay, and are having 4 cone types. So this means that the birds are much better than us at perceiving wavelengths in this visible color range. And also we are seeing that the birds are having quite nice uniform distributed peaks. Okay, so from here we can conclude that actually the humans are consistently more sensitive at what happens in the green and red, and is picking also some information in the blue wavelengths. So here is what the humans can do, but the birds are doing better than probably. And the other living beings that are equipped with vision, okay, may have some slight variations. So most of the living beings will have 3 cone types and will be able to capture a visible spectrum of wavelengths that is not so different than what the human can achieve. But others, like birds, can see more. Okay, so this has also some name, trichromy and tetrachromy. And actually what is interesting, this is also like a genetic disposition. There are humans that are having 4 cone types and they are tetrachromatic. Okay, but it's like a very rare condition. Okay, so now if we are moving from visible range that typically we have also captured with our cameras for taking pictures, videos, okay, we are looking also in outside in the infrared, and then we are getting some thermal images. Okay, and here is just a depiction of the visual RGB image and what looks like in the thermal or infrared. Also, we can use the near infrared or thermal images, for example, in satellites, and is giving us some information about what happens, let's say, crops or vegetation on the soil, and so on. So, bottom line, we have electromagnetic waves. We are sensitive to reduce range, the visible spectrum, and there are quite a number of electromagnetic waves or wavelengths we are not sensitive to, but we can get sensors to give us readings in that. And depending on the application, we may make use of the extra wavelengths that are out there. However, in order to be successful at what the humans can do with their vision, we should be able to devise algorithms that are handling the visible spectrum as the humans can do. Okay, so now if we are moving to the interaction with the matter, the interaction of the light that is coming from some source, for example, the sun, okay, we have 4 types or phenomenon: absorption, scattering, reflection, and refraction. So, and in addition, eventually we can consider diffraction. So for absorption, we have like a prime example, the blue water. So the water, the deeper it is, the more bluish looks like. Is one example of absorption because the water is absorbing most of the wavelengths, and what is surviving is in the blue side or ultraviolet side of the spectrum. Okay, the scattering, we have the blue sky or the red sunset, and we will see what means scattering in the next slides. Then the reflection, and the example is the colored ink. So we are just getting reflected some wavelengths that in the end is telling us the color of that substance or matter, and the refraction. And our prime example is the dispersion by appraise. So let's look at the scattering. So the scattering is an interaction of the light with the matter, and it depends on the relative sizes of particles. So the matter in the end is formed from particles. At the basis, we can consider the atoms, the molecules, but also we can have larger structures in the matter, and the wavelengths. The wavelengths, okay. If we are controlling the source of the wavelength of the light, then we can estimate, and we know what is the matter, we can estimate the effect, the wavelength the light has to the matter and how it interacts. Okay, so if the wavelength is relatively higher or larger than the particles in the matter, we are in the case of so-called raylight. Okay, and this means that if the wavelengths are relatively very large compared with particles, then basically everything that comes from the light can go through the matter, through the particles of the matter, okay, and nothing will be reflected, or nothing is a interaction between them, because the wavelength will just be large enough just to go beyond the sizes or of the particles. Okay. What is quite interesting is when the size of the particles is comparable with the wavelength. And then we have a so-called Mie interaction or Mie scattering. Okay, and here we are getting all kinds of interesting results, because the wavelength interacts directly with the particles, and we can see some alterations of the light. Some wavelengths are absorbed, some are reflected, some are refracted, and so on. And the third case is when the particles are much larger than the wavelengths. Then this means that actually the wavelength or the light could be stopped in the particles, cannot go through the matter, okay? And we are in a so-called non-selective case, but let's see probably a little bit more about what means scattering and interaction and what means wavelengths. So this division of what happens with the scattering, okay, is mainly based on the wavelength and the relationship between the wavelength and the size of the particles. Okay, so if we are marking here the wavelength, and the wavelength goes from left to right, okay, from small to high wavelength, and we are considering here to be the size of the particle, this S, okay. So we said that if the wavelengths are larger than the size of the particles, then we are in the raylight scattering. And if the wavelengths are considerably larger than the particles, then basically the wavelengths are not affected by the particles. And then we are not getting any scattering of the energy. So it's no interaction, strong interaction, and everything just goes through. Okay, so this is at the extreme of the raylight scattering. When we are getting comparable wavelengths to the size of the particles, then we are entering in the area of so-called Mie scattering. And the more comparable with the particle it is, the more scattered energy, because we have the wavelengths of the light that are fully interacting with the particles. Okay, so here we are getting quite a bit of energy that is absorbed by the particles and in this interaction. Okay, and here what is not shown is the other case where at the extreme, if the wavelength is much lower than the particle size, okay, then the wavelengths are practically stopped in the particle in the medium. So we are just getting all the energy of the wavelength moved into the matter, into the particles. Okay, so if we have high wavelengths or long wavelengths, okay, we have little scatter, okay, little interaction, and quite interesting here. This is a clear example. If we have a radar, typically the radar is using a very long wavelength. Okay, in this way can send the electromagnetic waves, and those electromagnetic waves will not be stopped, or the energy will not get scattered by matter like the atmospheric air or the clouds. Okay, and yeah, so this is like a prime example. Everything else are examples like sunset or sunrise. So for example, here we have the sunset, and we have a red effect. So the sun is the source of the light. The interaction is with the particles and everything that is in the atmosphere. So we are in the case of ray light and Tyndall effect. We are getting some interaction that typically means getting something reddish and some bluish, because the light is interacting with the particles that are in the atmosphere, especially the water particles. Okay, and if we are looking also at the atmosphere, if we are getting some clouds, the clouds are putting together large molecules of water. Okay, and tends to be more compact and dense, and then those are sufficient to stop the wavelengths. Okay, and we are in the case of non-selective scattering. Okay, and we are getting this kind of grayish clouds, the effect of this interaction. Then on the bottom side is the case of Mie. Mie, as mentioned before, is the case where the wavelengths in the light are comparable with the sizes of the particles. And here is a prime example for Mie, where we have in the atmosphere ashes or particles from a volcanic eruption, and those can be of comparable size. The particles in the air would be of comparable size with the wavelengths in the light, and we are getting this kind of effect. Okay, so let's move on to another phenomenon, the reflection. And the reflection, probably the most common and well understood, is the mirror reflection. We are getting a surface that is reflecting very well what is placed on one side of it. Okay, so typical reflections like here, we have just a still water lake. And we can see in the water the reflection of what is above. And here we have a very smooth surface and something placed on it, and we are just getting the reflection in that smooth surface. Okay, so for a mirror reflection, here we are just distinguishing between two media, media 1 and media 2. Typically we have air and water, or air and some other material. And each media, okay, will be characterized by some reflective index. N1 and N2. Okay, so this in the end depends on the material, depends on the kind of particles that are out there. Here is just a simple briefing about what means reflection. So if we are in this case and we are getting some source to light on, let's say, in the first medium, and we are having a incidence of this light, okay, we are just taking with green the incident and the reflected light, okay, and we are marking here with N a normal, so this means perpendicular to the plane surface that is in between these two media, okay. Then we can define a angle. So this is an angle of incidence that is defined between the normal, the surface, and the incident light ray. Okay. And we can define also a reflection angle that is between the normal to the surface and the reflection from this surface. Okay. So in the case of mirror reflection, we are getting the incident ray reflected back in the same medium, and the angle of reflection is equal with the angle of incidence. Okay, so this is the basic definition of reflection, and happens when we have two media and some ray, light ray, is not crossing in the other media, is turning back in within the same medium. Okay, so this is what means reflection between two media. And now, depending on the nature of the media we have, so for example, the second medium, if it's a dielectric, so this means that it doesn't conduct, is an insulator, doesn't conduct electricity, is an insulator. Okay, and we are looking here, we have some reflectance and angle of incidence. So again, angle of incidence is defined between the normal and the inciding ray. So if it's to look here, 0 corresponds to a perfect perpendicular to the surface, and 90 degree will correspond to a ray actually is parallel to the surface. So back, if we are looking at angle of incidence, we are looking from 0. So this means perpendicular to the surface, and 90 degrees, that means parallel to the surface. And we are looking here at the reflectance. So obviously, if it's parallel to the surface, the whole ray basically will not be, or will be very the least affected by the other medium, and everything, most of the energy will get back reflected. While if actually is a perpendicular incidence angle, okay, then if it's perpendicular, then the dielectrics tend to trap most of the light and reflect just a little back. Okay, so we are getting full reflection at grazing angles. So this means we are getting full reflection when the incidence angle, okay, is close to 90 degrees, and is basically close to being parallel to the surface. Okay, and the very little reflection, if we are getting close to 90 degrees to 0 degrees, and then the ray is just perpendicular to the surface. Okay, so if it's a conductor, then almost regardless the angle of incidence, most of the ray will get reflected back in the original medium. So the conductors are typically metallic surfaces. Okay, so this is the biggest difference between the nature of the second medium here, assuming that the first medium typically, let's say, is the air. Or okay, if the second medium here is conductor, typically we are getting a fully reflective mirror. If the second medium here is not a conductor, is just a dielectric, then we may expect getting a reflection only if the ray is almost parallel to the surface. Okay. Now, if the surface is rough, like in the B example here, then we can just imagine that the rays, okay, if they are coming from the same source and are almost parallel, okay, we'll just find all kinds of normal points, okay, because the surface is not perfectly plane. The normals will just vary with the position on the surface, okay, and then the reflection will happen at different angles. So if the surface is plane, okay, is smooth, then we are getting a reflection that is quite well behaved. We have a single angle of incidence and the same angle of reflection, and everything is aligned, and we are in the case of so-called specular reflection, because it's not changing the angles in the reflected ray. If actually the surface is very rough, we are getting this kind of diffuse multiple angles for the reflected rays, and we are in the case of non-specular or diffused reflection. So here is just a simple schema. So if we are getting a source, we are getting some light. This is like a depiction. If it's a rough surface, we are getting some diffuse reflection, and this diffuse reflection goes everywhere. The diffused reflected rays goes everywhere. While the specular means that the rays that are coming from a source are going pretty much with the same angle reflected. And we can be also in the case of a mixed. So this means that we are getting a group of reflected rays that are agreeing on some direction, and at the same time we are getting quite a number of diffused reflections. Okay, so those are the three types of reflection, and pretty much depends on the smoothness of the surface. And we looked here also a little bit about the nature of the second medium, if it's dielectric or is a conductor. Okay, here is like an interesting case. We have a wavelength, and for example, for a leaf, we have the lower and upper side of the leaf. Okay, and if it's to look at the reflections of the leaf and the wavelengths that are coming, let's say, from the sun and so on, we just see that actually the leaf can reflect differently on the lower side and the upper side and so on. Okay, this is just a depiction what you can see on different kinds of surfaces and materials and objects. that are in the surroundings. Okay, so what you must understand already here is basically we have almost always we have a source of light, so a source of wavelengths of rays, and the interaction of these wavelengths to matter, to objects, to surfaces will just create all kinds of reflections, scattering, deviations of the incident light or incident rays. Okay, and exactly these reflections, scattering, and the way is interacting with the matter is the one that is bringing us the information. So if we are getting like a very nice aligned reflection, already is telling us that we have a reflective surface. In the way actually is behaving on a rough surface, and if the wavelengths are in some ranges and so on, is telling us about the color. The color in the end is connected to the wavelengths of that surface, and something about the nature of the material. In the end, here we were mentioning about flat and rough, but in the end, if we are looking at some edges for some objects, that is just a interaction in a smooth surface, right? Okay, so we are just getting also a change of angle. That change of angle in the end is something that we are perceiving just by looking at reflected lights. Okay, so our vision is based on this interaction of the light with the matter. And the way is interacting and how much is reflecting, how much of the wavelengths are absorbed, which wavelengths are reflected back, will just give us information about what is there. So if we are looking at some, let's say here we have a butterfly or whatever other object, and we want to be able to fully describe what will be the resulting reflection, or if we are coming with some source of light and we are exposing this butterfly to that source of light, and we are interested in seeing the wavelengths and the way actually this butterfly looks like after exposing to that source of light, then basically we need on each point on this surface of the butterfly, we need a so-called bidirectional reflectance distribution function. So pretty much we need in each point some information about how the surface is reflecting the light. Okay, the bidirectional reflectance distribution function defined in each point. And if we know in each point, then yes, given any source of light, we are just using this information and we can know whatever appears in each point in this butterfly for that source of light. Okay, so another interaction with the matter. So far we have seen a scattering, reflection, and now we are looking at the refraction. So this is a prime example of refraction. So if we are placing some pencil in some glass with some water, we are having a transition between the air and the water media. And we are seeing here a disruption, okay, a discontinuity, and is coming from refraction. So we have two media, we have two indexes that are describing or characterizing these two media, N1 and N2. Okay, we have some source of light, we have a ray that is coming, is reaching the surface or the separation surface between two media. We have the normal to the surface, N. We have this inciding ray. Okay, we have the incidence angle defined between the normal and the inciding ray. And we have the reflection. So now the ray actually goes through the second medium, is not reflected in the original medium, goes to the second medium, and goes to the second medium with some angle from the normal. So we just imagine that we have the normal, and we are defining here a refraction angle. Okay, so we have a law that is putting in relation the incidence angle and the refraction angle with the indexes of reflection for the two media. So is this simple formula here that is telling us what happens there. So given the indexes and the inciding angle, then we can compute the refraction angle. Okay, so to be more complicated, typically the refraction is not just a simple change of angle of direction for the light, for the ray. Okay, this is combined also with the wavelength. So if the original ray is white light, for example, then it's a combination of multiple wavelengths. Depending on the wavelength, okay, we may get different refraction angles. So the refraction is more complicated than a mirror reflection. The path orientation of light rays is changing depending on the material and the wavelength. And exactly because of this refraction and these properties, that the wavelength will have different refraction angle, depending also on the material, okay, is used, for example, in a prism. So prism typically is like a glass, okay, with some shape, prismatic shape, okay. And if we are getting a light, white light, okay, then using these properties that we know, we have some media, for example, whatever is the glass or plastic or some other material, okay, then already at the entrance of this ray through the prism will be a separation of the wavelengths at different angles. And then when it's going out from this prism back to the air, to the original medium, will happen another refraction, and the wavelengths will get even more separated, spread out. Okay, so basically the refraction is defined like this. For a given ray of some wavelength, we are getting this formula and everything is fine. But if actually the ray is a combination of wavelengths, and typically this is the case for sources of light like the sun or white source of light, okay, then basically the refraction is combined with some dispersion that happens in the material. Okay, and what we discuss here is also the principle of the prism as a separator of the wavelengths in a light, in the light ray, let's say the white light. Okay, so we have seen scattering, reflection, and refraction. Now let's look a little bit at the absorption. So as mentioned before, when it's coming to the scattering, we were saying that at some point the particles are too large and the wavelengths are too low, and then actually is a non-selective absorption in a sense of the light, so it's no big scattering that is happening there. Okay, so when it's coming to the absorption or the dissipation of wavelengths, this also depends on the medium. And for example, here we have an index of refraction. It's the same index of refraction that we use for refraction between two medium. And here we have based on the resonance frequencies of the molecules that is in that medium, we have some peaks for the refraction that is happening there. So basically, the absorption is happening when the wavelengths are aligning to the resonance frequencies of the molecules. Okay. And out of this interaction, some transfer of energy happens. The wavelengths are getting absorbed, and typically is, yeah, you can just see is like a thermic effect. If you are exposing to the light and you are absorbing everything, you are just getting warmer. Okay, so this is what happens with the absorption. If we have absorption, we are not getting back some information. So this is not good for vision. But yeah, it still is an information. Okay, so if we are looking at the human sensitivity, I remind you that we have three cone types. One cone type is more sensitive to the blue, somewhere around 400 nanometers. Okay, and some other two cone types that are closer to what we call green and red. And green and red cone types are closer to 500 nanometers. Okay, so the spectral composition of light above atmosphere. Here we have like energy and the wavelengths. We just need to look at the measurement. So basically, we have from 200 to for a visible spectrum around 300 and 760 somewhere here. So this is what we have like a visible spectrum. And here we are just showing a little bit what means the energy and the interaction and the spectral composition of the light above the atmosphere and spectral composition of light below atmosphere. Some wavelengths get strongly weakened due to absorption. So the good thing is at least we are looking, or we are sensitive in a range of wavelengths that are also carrying most of the energy after passing through the atmosphere. Okay, so this means that we are fit to the Earth conditions. Okay, so this was about the light and the interaction with the matter. So I propose to take a break and get back at 11:30. Do you have questions? If you have questions, just unmute and let me know, or just drop into chat. So we'll resume at 11:30. Okay, so let's continue with acquisition of images and what exactly means this. So we'll focus on illumination and cameras. We have again the scheme. We have a light source, surface, the interaction between the light and the surfaces or the matter. And on the other side, we have the camera with a sensor array, some lens system, and a formed image plane. Okay, we discussed a little bit about what means light and the interaction with the matter, and how the light is helping us to see. And now we'll focus on the illumination first and move on to the camera and how the images are acquired. So illumination. Well-designed illumination often is key in visual inspection. So if we want to see something, better provide the right illumination, the right kind of light that is facing the material or what actually we are expecting to see. So we have quite a number of illumination techniques. And these illumination techniques are in the end simplifying the image processing because are controlling the environment. So controlling the illumination, controlling the light source, we are controlling actually what we are seeing as interaction with the matter. So if we are in a controlled setting, it's very important to make use of everything that we know about the matter, the object we want to see, and whatever is there to inspect, cracks or color or whatever other things, and to understand exactly the kind of illumination technique that we want to apply. We just need a normal light source, or we just need some specific wavelengths. Okay, so here is an overview of illumination techniques. And I will just go quite fast with them. So backlighting. So for example, if we are placing some lamp or source of light behind transmitting diffuser plate. Okay, so the other way around, if we are getting a backlighting, as the name says, we are placing some light source behind some object. And if that object, for that object, we want to analyze, for example, the silhouette or the extremities, the boundaries of the object, if we are placing the light source on the other side, okay, we are just getting a very good contrast on the boundary. And we can therefore get some binary vision. So segmenting that object from surroundings is easy. So for example, here, an example of backlighting, we are just inspecting some glass bottles. Okay, and if we are placing them, the light in the back of these bottles, we can get quite nice contrast and a clear separation of the bottle from the surroundings. Okay, then we have directional and diffuse lighting. So for directional lighting, we can generate sharp shadows, generate specular reflection, for crack detection, or also we can generate some shadows, and shading will yield information about the shape. Otherwise, if we are using diffuse lighting, we are illuminating uniformly from all the directions. And in this way, we are not casting shadows, and we are not obtaining large intensity variations, especially on glossy surfaces. So, for example, we have a crack detection. We just need to direct the light to at the right angle and place some sensors or receivers, okay, also at the right angle, and depending on how the reflection happens, we can detect if the surface has some crack or not. Okay, this is quite standard, used for some electronics, PC boards, and so on. We can also use diffuse lighting and so on. Okay, another illumination type is lighting with some polarization. So typically is used to improve the contrast between Lambertian, diffuse, and specular reflections, and also to improve the contrast between dielectrics and metals, so dielectrics and conductors, and especially when inspecting electrical circuitry. So the polarization is one of the electronic waves, okay, electromagnetic wave, and typically is just defined by a angle, okay. And how we are controlling this? We can adjust. We have a control in the source, and based on the polarized light and how actually interacts with the matter, and how this polarization is maintained or exchanged or changed by the interaction, we can deduct or infer different things. Okay, so we can have also a look at basic models of reflection. Already we have seen in this hour. We have a purely diffused, a source, and we are getting light everywhere reflected. The specular reflection, everything is grouped along one direction in the reflection, and mixed. Okay. In the polarization, we can have a source. We can have like a filter that is selecting just some angles. Okay. Then we have our interaction with the matter. And then we have an analyzer. So based on the interaction, okay, first is the filtering, or getting the polarization angle and what we want to have in the illumination, in the lighting. Okay, and the interaction with the matter, we are getting some information at the receptor and analyze that. Okay, so I'm not entering in the details and so on, but this can be quite useful in all kinds of industrial checking of the materials. Okay, so then we have the colored lighting. So obviously, if we are interested only in some wavelengths and some color properties of the materials and so on, we can just isolate some wavelengths or filter as a light source to get only some wavelengths. And we can, moreover, do all kinds of pattern lighting if we want. And yeah, then by looking at how the material or the surface of the object and so on is interacting, we are just getting some information related to the color or to the pattern and so on. So we can just check some components if we know their colors, and we are just using some light that is matching. And in this way, we are getting a good segmentation of those colored components. So when it's coming to structures and stroboscopic lighting, we can just, from the beginning, control the light and place some patterns that are known, okay, in each, and let's say the way the pattern is formulated, if we are looking at the resulting reflection or scattering of the material and so on, we can use the information to do some geometric analysis or not. Okay. When it's coming to stroboscopic lighting, typically means beams, some high intensity light flash, and are typically used when we are getting some motion. The objects or whatever we are inspecting is moving with some speed, and we can just have a stroboscopic lighting and get some high intensity light flash for a short time, and reading also in that short amount of time. And this will just eliminate part of the blur that typically is seen for moving objects. Okay, so if it's moving, we are getting something like this, but if it's stroboscope, we are just getting a short, high intensity light, and it's just helping. Okay, anyway, so those that was just a discussion about the illumination techniques. Okay, the most known and used technique is the one that we are just by default assuming we have some light, typically white light source, okay, sun or some other bulb, light bulb or whatever that are commonly encountered, and having this light source, this illumination, we are getting some interaction with the matter, and then the reflections, the scattering, this interaction is captured by a camera, and in the way the camera is working with this reflected light will create some image, and this image will have an interpretation in our visual system. Okay, typically the image is supposed to reflect entirely what happens in the scene. Let's see exactly what happens there on these cameras. Okay, so camera models. So first, a little bit about the optics for image formation. The most known and the basis model is the so-called pinhole model. So assuming that we have a camera, this cube, we have a small, okay, opening hole, okay, on one side of this cube or camera. Okay, then through that hole will enter some rays that are coming from the objects or whatever is in front of the camera. Now, if we are just doing simple geometry and we are just marking there the rays that are potentially are coming from all the points on this object in front of the camera, then we are seeing that on the opposite side of the camera, an image could form and this image actually will just be upside down. So this is just simple geometry. If we are just allowing here a hole, we are placing in front some object, we are tracing some rays through this hole. Okay, then the projection on the backside will just be something that is upside down. Okay, and the pinhole model is one of the first to be used. And yeah, at the beginning, the name for the pinhole model and the created camera was camera obscura. What means this was really a camera, a room, okay, and was obscura in the sense of lacking light. So in this room was no light and was just a small hole through which we were getting the rays from the front of the camera. And these rays were going through this hole in the camera obscura or camera dark room, okay, dark camera obscura. And these rays were carrying the information of what was in front and eventually were imprinting on some photosensitive material. That was a sensitive material typically was some sort of solution, chemical solution that was photosensitive and was requiring some long exposure to produce some change. Okay, so this is about the origin of the name camera. Basically, the origins really was like a room, and in Latin, camera means room. Okay, and originally was obscura because it was a dark room, and the source of light or the light information was coming through the hole to expose or to imprint some support or some solution that was photosensitive and was in the end capturing the image, the formed image. Okay, so if we are looking at the optics, and this is just a simple depiction, so we may assume that we have axis, a coordinate system, x, y, z. This coordinate system is placed in the hole of the pinhole model. Okay, and in front of the this hole or in front of the camera, we have an object O, and we can just get some point on this object. And this object has this surface. The point is lying on the surface of the object. And if we are looking in the back of the hole, we are getting the plane where the image is formed on the back hole, let's say, of the camera or of the pinhole model. Okay, so we have the hole, and at some distance, f, a focal distance, we have the image plane where the image is supposed to be formed of whatever is in front of the camera. So now if we are just taking the points on this surface from the object, and we are assuming that from those points we have some rays, light rays, okay, that are going from there and are crossing the hole, then we'll just get projected, or it will intersect the plane, the image plane, for example, and we are marking here with PI. So the point from the object gets to the point on the image through the hole of the pinhole model. Okay, so if we are looking at simple geometry, if we are looking at the coordinates of the points on the object and on the image, then we are seeing simple relationships. So all the points that are on the image, okay, if we are taking the x coordinate and y coordinate, and we are dividing the x coordinate on the image with the x coordinate on the object, or the y coordinate on the image and the y coordinate on the object, we are just saying here that the ratio is the same. And if we are just taking also the the distance from the hole to the image, this f, or focal distance, okay, and the distance from the hole to the object, okay, then we are getting this set of ratios, and they are equal, and are equal with minus m. Okay, so this ratio in the end is giving us a measure of linear magnification. So typically the camera is much smaller than the distance between the camera and whatever is the object in front. And we have there some proportions between the x, y, and z coordinates. And this proportion is the same, equal with some linear magnification that is happening in this camera. Okay, so this is the very basic geometry for the pinhole model. So yeah, we can just now typically the pinhole model is just assuming that is a small hole and everything is going through. The thin lens equation means that we are just assuming here in the hole that we have some lenses, and we'll see exactly what means this. So instead of letting the rays to go through some small hole and project in the back, we can add some lenses, and those are giving some extra flexibility. So it's not anymore just one ray, and whatever is going through that small hole that will be in the end used to imprint in the image formation. But with the lens, we can have a bigger hole and therefore put together multiple rays that will form in the end image in the back. So we can just convert multiple arrays. So if we are just looking here, the original model was pretty much saying, okay, we are just getting a small hole, some origin here with O, okay, and one array was going from the object and was going through this array and creating a single point for that array that is corresponding to the starting point on the object. Now, basically, if we are having a lens instead, okay, then we can get multiple rays from that point on the object that are getting to the lens, and through the lens, we are getting the properties of the lens, okay, refraction, and by controlling the curvature and the lens itself, we are getting all these rays that are going from this point on the object will just go in the same point on the formed image in the back. Okay, so now the lens are capturing more light than the hole or the pinhole model like it is here. Okay, and this will happen if we have spherical lens surfaces, okay, and the incoming light is more or less parallel to the axis, and the thickness is much lower than the radii. Okay, and the refractive index is the same on both sides of the lens. So you remember what means refraction. So if is the same refractive index, will just give us this nice property of finding a plane where all the rays that are coming from one point on the object will just get united back in one point on that plane in the back. Okay, so now if we are looking at the simple geometry here, so this f, the focal length before, okay, now it's not just the distance to the plane, the projection plane, where the image was formed. Basically, it's a distance from the centrum or the origin of the lens, okay, to the middle distance to the plane where the image is formed. Okay, and if we are just putting down the mathematics, we are getting this relationship where 1 divided by the z, or the distance from the lens to the object, minus 1 divided by the distance from the lens to the formed image, okay, is equal with 1 divided by the focal length. So the main advantage of the lenses is simply like this. We are capturing much more light than the pinhole model, and this gives quite a increased robustness, and helps quite a bit. Okay, so now if we are looking at the lens and we are placing some object, okay, on one side, and we are getting some image point on the other side, and so on, okay, so we can have our object, and we can trace some rays, okay, to the lens, and see if these rays are forming on the expected image plane or not. Okay, now the thing is, if we are placing this object at a smaller distance or at a higher distance in front of the lens, we may get that our projections or our points that are supposed to form on the image may be placed in front or behind the image plane. So if we are just defining simple like this, we have our object, okay, and we are just taking some other placement, minus here. We are getting some distance in front, and we are looking at the distance that is produced in the projection. Okay, we can just derive and see exactly how big is the distance in front between the placement of 2 points, and this will correspond to how big the variation, let's say, in the position of the points that are in the image plane, in the projection. Okay, so in the end, the whole depth of field idea says simply like this: depending on the lens and the camera, and okay, some points will be projected in some reduced area on the expected image plane where the image is formed. Okay, if actually the distance or this Z interval, depth distance from the camera, from the lens, is exceeding something or is quite large, then we may get a spread in the projection of the rays, okay, in the image plane that is quite large. And if this spread is quite large, we end up that actually we are getting a blurred exposure in the image. So basically, the depth of field in the end is a relationship between the sharpness of the image and the interval, the depth interval where the object can be placed in front of the camera. Okay, so the depth of field and the dimensions of the lens and so on, okay, are supposed to be placed in some balance such that to get some reasonable sharpness. Okay, so we can do for placing a point that is closer to the lens, to the camera, or something that is further away, and we are getting a similar equation for those two. And in the end, we are interested in this spread on the image, this B, okay, and the depth, the width of the lens. So in the end, the depth of field, we can just adjust it by playing with the lens and adjusting the aperture and what happens on the camera. Okay, so if we are looking at the lens model, that in the end is assuming that we are having this nice property that all the rays that are coming from one point on the object surface are ending up being in one point on the formed image. Okay, then we have obviously deviations from this lens model, and we need to correct them in the real camera devices. So we have three main assumptions. All the rays from a point are focused on to one image point. All the image points are in a single plane. So all the rays are going in a single, from one point are going in a single point. Moreover, all the points that are in front on the object, for example, are supposed to focus on the same image plane, so are in the same supporting image plane. And where the magnification is constant. And I'm just going fast. So we had this kind of relationship about the magnification. So obviously all of those are three assumptions, are good to have, ideal to have, but are quite far from ideal. And therefore we have some aberrations or deviations of the lenses. So these aberrations, we can divide them into geometrical and chromatic. Geometrical are visible as image distortions or degradations, like blurring. And when it's coming to the chromatic, we are just saying a different behavior for different colors or different wavelengths. Okay, so we are seeing in the color domain what happens. So for geometrical, typically if we are getting something that is paraxial, so it's quite, okay, let's go back. So this Z direction is also called optical axis. So the paraxial rays are those that are coming very close to this optical axis. Okay, so the geometrical aberrations are quite small for those that are very close to the optical axis. And if we are looking at the chromatic, everything is a relationship with the refractive index and the function to the wavelengths. And we have seen before what means this refractive index, and how actually the prism is separating the wavelengths because the material is reacting differently with the different wavelengths. Okay. So now how to correct those or to reduce them? Well, typically we are relying on some composite systems, multiple lenses, multiple complementary materials that are helping to control and to reduce the chromatic and the geometrical aberrations. So if we are looking at the geometrical aberrations, here are 4 such aberrations. We have the spherical aberration, astigmatism, and radial distortion, and so-called coma. The most important, and also one of the most occurring, also in our nowadays devices, is still a radial distortion. So let's see first the spherical aberration. So in a spherical aberration, we have the lens. And what happens here, the rays that are parallel to the optical axis do not converge after going through the lenses. So instead of converging in the same point, are just getting quite a spread. So we can see such effect, for example, here, if we are just getting some expected convergence in some points, clear points in our image. And if we have spherical aberration, then actually we don't get this convergence, then we are getting a spread like here. And this means that on the formed image that is supposed to be somewhere here, okay, we'll just get some projected rays that actually are not coinciding with what is the expected position. And then we are just getting this spread, and this spread, okay, is quite visible here. And this marks the spherical aberration. Okay, the radial distortion, and here we are just showing for one photo without radial distortion. So we are looking at the geometry of this building, and everything is clear and clean. Okay. However, if we are just getting some radial distortion, we may get different magnification for different angles of inclination. So typically in a radial distortion, we are getting either an effect like a barrel. So we are getting some curvature, round curvature to everything that happens from the middle point in the image to the outer points. Okay, or something like a pincushion, like here, we have the middle point and everything is just getting some curvature that is coming from out to the middle. Okay, so this is a simple naming of the radial distortions that are caused by different magnifications for different angles of inclination. And yeah, in order to model and to also compensate for this, typically we are just assuming that we have the central image and everything is centered on the image, including the radial distortion. And then we have a multiplicative factor on the pixel location depending on the pixels distance to the center. So we have R, some distance to the centrum. Okay, and this D will just be something that is a relationship between some coefficients and the power of the distance of that pixel to the centrum. Okay, so this is what is considered to be a multiplicative factor that is affecting all the pixels at some distance R from the centrum. So most of the time and most of the effects radial distortion is symmetric, and we are just taking into consideration just the distance to the centrum. Okay, how to correct this aberration? Well, typically, we can correct this easily. It's just a simple mapping of the pixels with relationship to the centrum. Okay, we correct them if we know the parameters, K1, K2, and so on. In order to find out the parameters, then either we know the camera and is known the K1, K2 from whatever, the design of the camera and the people that worked with that camera and sensors, okay, and we have them, or we can just do some sort of analysis. If we are getting some images, and for example, we know that in that image are supposed to be some structures, and those structures are supposed to be straight lines or straight segments, we can just identify these lines, and based on those lines and their relationship to the centrum and so on, we can just try to estimate these parameters. And after estimating these parameters, we can just compensate and get a undistorted image. Okay, when it's coming to the chromatic aberration, so we have a different behavior depending on different wavelengths. So if we are looking at the lens, the lens in a sense can act like a prism and can just spread some incoming rays in some different wavelengths, okay, and then this may end up obviously behaving differently, and we'll get different projections where it's supposed to be formed the image plane. So a typical problem for chromatic aberration is something like this, that the lenses are not perfect, are coming from some materials, and if we know that some material is providing some chromatic aberration or is leading to some aberration, we can just come with different materials and try one material to compensate the problems of the other material. So achromatization is achieved if we are pairing or combining some different glasses, some different materials that are used for lenses. And then with this kind of achromatic lenses, okay, we may get something that is producing better images. Okay, so this is about about aberrations. Now, just a very brief overview about technologies. So nowadays we have two major technologies for the cameras. Those are CCD and CMOS. CCD stands for charge coupled device, and CMOS, complementary metal oxide semiconductor. This CMOS actually is the dominating technology. Probably 99.9% of the cameras devices are using the CMOS technology. I'm not going to enter in the details about the technology. I'm just pointing out that those are the major technologies for the camera sensors. And the CMOS is more reliable and cheaper at the moment. And here is evolution, for example, from 2010 to 2015, about the units, camera units, and their mega number of pixels, megapixels, okay, and resolution, for example, VGA resolution 1.3 megapixel and so on. And we are seeing that is a general tendency of getting higher and higher resolutions, because also the technology is evolving and the price is dropping. So we are getting a higher and higher number of pixels, and this is perfect. So CMOS in the end assumes, this is something that you need to know, CMOS assumes that we have a grid, and over this grid we are getting some cells. In each cell actually is a pixel, and for that pixel reading we are getting some electronic support. Okay, a small sensor for that reading in that pixel. Okay, so when it's coming to megapixels, is pretty much how many such integrated circuitry can be placed and get to this kind of image over a grid. Okay, so just placing side by side, yeah, the CMOS are largely is the main technology nowadays, is placed also on consumer cameras everywhere, is cheap, low power, has a problem with sensitivity, but anyway, it's compensated by the chip, the technology, the per pixel amplification, random pixel access, smart pixels, and the integration with the other components. So pretty much the whole technology is around CMOS nowadays. While the CCD is still applied in some niche applications. Okay, so in 2015, Sony was announcing stopping the CCD and so on. Okay, when it's coming to color cameras, we have three concepts. One is based on prism, another one is for filter mosaicing, and one is for filter wheel. Let's go quite fast. So assuming that we are getting some light that is coming through our lens or whatever is the optical filter, okay, we are ending up to the part where we are forming the image to the sensors. So in the prism color camera, basically we are getting the input image, the input ray, okay, and this is getting through some prism that is in the end formed by three materials or three prisms that are tightly connected, such that one of them to separate the red wavelengths, the other one the blue, and the other one the green. So basically we are getting this mechanical optical sensor, okay, to separate the blue, green, and red components of a input ray. Okay, so that is like the basic idea of the prism color camera. Okay, another way of ending up to RGB or the decomposition of the color is to use a filter mosaic. So what means this? Means that in the back we have about the same technology, let's say CMOS technology, over some grid, and on top of it we have a Bayer filter. So this means that on top of the grid we can just place some filter that is just allowing some wavelengths, for example the red, the green, or the blue, to pass, and then yeah, we are just getting red, blue, or green readings in each of the pixels on the grid. So here is just some depiction. We are getting the micro lenses or some simple filtration of the light. Okay, then we have a color filter array. Okay, and this color filter array is just filtering in each of those is just filtering some wavelengths for green, for blue, for red, And in the back, we have just a sensor substrate. So that is of the same time in each point. Okay, and it's just capturing, counting the photons that are crossing these filters, and will just have the expected wavelengths. Okay, so color filters lower the effective resolution because he's imposing some filters. So the micro lenses often are added to gain more light onto small pixels. But yeah, depends on each technology. Another way of getting the RGB or the decomposition wavelengths in each pixel is so-called the filter wheel. So this means that we have something like here that has like a small hole, and in the back is something like a wheel that is moving with some speed, and basically it's just putting some filter for some color band at any given time. So if we have a static camera, the static scene in front, then at each time we are just getting different wavelength reading because it's filtered here, okay? And we are getting a composite image. At each time we are just getting some color bands. Okay, so this is the filter wheel approach. Okay, nowadays the most common is a mosaic. We have the same kind of sensors, and because it's cheap, we have a high frame rate, and we can correct plenty of things. We can just work with them quite easily. And yeah, anyway, the wheel and the prism technologies are still used, especially for expensive and scientific applications. Okay, so now if we are looking at the geometric camera model, but maybe it's better to take a break. Okay, so let's take a break and get back at 35 past 12. So if you have questions, just let me know. Okay, so let's continue. We have seen a little bit about what means technology, the sensors. And now let's look again at the geometric models for a geometric camera model and perspective projection. So if we are looking at the pinhole model, we have some object in front of the camera. We have a camera, we have some small hole, and we have a forming image. So this is the real image inversed. Okay. And now if we are revisiting the pinhole model, we have a center of the lenses, the center of projection. We can just consider that we have here, and we are adding a virtual image plane. Okay, that is in front of the camera this time. Okay, and this now is similar to the object, to whatever is in front of the camera. Okay, so this is the pinhole model revisit. And now we have a perspective projection to obtain this virtual image plane. So this was the scheme from the past few hours. We have a light source, we have the surface of the objects, we have the rays that are crossing the lens system or the hole, and we have some sensor array in a camera, now this camera. Okay, and we have some image plane. So this is actually the virtual image plane. So the equivalent to what we have here in the revisited pinhole model. Now, so if we are looking at the perspective projection, what we have? So this is the image plane, the center of projection, and we have some object in front. X, Y, Z are our axes. The center of the projection is placed here, where was the hole. Okay. And now the image plane or the virtual image plane is placed in front at F focal distance. And we have UV coordinate system for the image plane. So the center of the projection goes in a principal point in this image plane and is along the optical axis, the Z. Okay. And then if we are taking some point on the object in front of the camera, this point, from this point, we can have some rays that are connecting the center of projection or the hole of the camera or the central point of the lens. Okay. And by connecting this point on the object with the center of projection, we are intersecting the image plane and we are getting there also a point in the image plane or in the virtual image that will have a UV coordinates. Okay, so the origin lies at the center of projection, the center of the lens. We have the Z axis that coincides with the optical axis, and we have the X axis that is parallel with the image plane, with the image plane rows, and Y axis that is parallel with the columns. So now we are getting closer to the typically manipulated 2D images that we are obtaining from our digital cameras. Okay, so if we are writing down some formulas, then we have a relationship between the u and v on the image plane and the x and y and z coordinates. And this relationship in the end is intermediated by f, the distance between the image plane and the center of projection, and also a focal distance. Okay, so now this is a pseudo-orthographic projection. If we are considering that z is constant, so this means the distance of the object from the camera is constant, then we have x and y, okay, in the image we can consider, or if we are making this notation, we are having u and v basically directly with a scaling factor, the x and y coordinates, the original coordinates. Okay, so if this that is the focal divided by the distance on z-axis, okay, if this k is equal with 1, okay, then basically the u and v is pretty much coincides with the plane of the object. Okay, everything else is a scaling. And however, in most of the cases, the object is considered to be at some distance from the center of projection. So if it's at some distance, then all the points on the object will be approximately at the same depth distance from the center of projection. And if this is the case, then we may consider that this ratio is constant. So the objects are small compared to their distance from the camera. And yeah, this is a common approximation that is used. Okay, now if we are looking at a pictorial comparison between pseudo-orthographic, so basically what we defined here, and the perspective, we are getting something like this. Now, I'm going to the projection matrices. The perspective projection model, like was defined, is incomplete, but we can have 3D coordinates specified in our world coordinate frame, and we can have image coordinates expressed as row and column numbers. So basically, we have what is here. We can come with some world coordinate frame for 3D space. So you can just imagine some coordinates, some other reference. Okay, and we can consider that the image coordinates x, what we have here, u and v, will just correspond to the row and column numbers in the image. And yeah, so if we are considering those, then what we have. So let's go back to UV, the image plane that we are assuming. And here C is the center of the projection, or the centrum, the whole of the pinhole model, or the centrum of the the lens. Okay, and we have some coordinates, this R1, R2, R3, that are the one of the camera placed in that centrum. Okay, we have our coordinates u and v in the image plane. U and v is supposed to be parallel with R1, R2. Okay, and we have some optical axis that is supposed to be in the R3 direction. And this R3 direction is aligning with the Z coordinate for the points. Okay, if we are considering that we have a world coordinate system, this one that is marked here with 0, x, or y, z, okay, and the world coordinate system now we are just considering the points that are X, Y, and Z. Okay, and this is the camera that we have. And this is the image plane that we have. So the camera has this as optical axis, R3. R3 is perpendicular on the R1, R2, and also perpendicular on U and V. We can just write down these formulas where U and V is also placed in relation to the F. So it's pretty much the formulas that we had before that were connecting U with X, Y. So U was with X and some Z, and V with some Y and some Z. Okay, and then we were just making the assumption that Z might be approximated as being constant if the object is placed at an equal distance or is much smaller than the distance to the camera. Okay, so we are getting these relationships, and we can just write more like this. So we are still having the F, that is the distance between this C and where is placed the image plane. Okay, and the new formula that is placing in a relationship with the world coordinate system that is marked here with red. So now we have the X, Y, Z in our world coordinate system for the points on the object. Then we have the C that in the end are the centrum of projection from the camera. And we have U and V that are the coordinates in the image plane. And R1, R2, R3 that in the end are the coordinates or the axis of the system that is placed in the camera. Okay, so we have this kind of projection matrices that is placing everything into a relationship to the world coordinate system. Now, if we are going further and we said, okay, what if the image actually has rows and columns? So we have the pixels that are discrete over a grid, and we have rows and columns. And we know that these pixels, rows and columns, somehow we need to overlay them over U and V, what we have in this coordinate system. So we can write something like this. We have X that is corresponding to U. Okay, and with some adjustment from the V, and placed in relationship to some origin here. So basically we are writing the image or the pixel coordinates in the image space as being X and Y. Okay, and we are writing them in relationship with X0 and Y0 that are placed somewhere here in this image. And then we are just getting this Kx that is giving us a number of pixels per unit length horizontally. And we have a Ky that is giving us a number of pixels per unit length vertically. So basically we are proceeding to some discretization. We have the U and UV, okay, and discretizing by imposing the grid of pixels on top. Okay, and we have this S with V. S is indicating a skew, how much it deviates from a rectangle. So if we have a skew in the cells that are in this grid, so the skewness of the pixels in the end. Okay, so typically this S is just 0. We have nothing to concern about, and we just get a simple discretization, columns, rows, with some starting points. And we are ending up with pixel coordinates, X and Y. Okay. So often only the integer pixel coordinates matter. We are not going in a continuous domain. Then if we are reporting the pixels per unit horizontally, pixel per unit vertically, one to another, we are getting an aspect ratio. Okay. And the deviations indicate non-square pixels. Now, if we are looking at these parameters that are controlling here, so K parameters, S, the skew, and the starting points. So those are in the end what we call internal camera parameters. So basically, when we have a digital camera, we know from the manufacturer the internal camera parameters, because in the end, he's just telling us how many pixels, what are the sensors there, and how the image is formed. And we just need to know those in order to have a mapping between the image plane, UV, and the pixel coordinates. Okay. If we know all of those, then we know that is internally calibrated, the camera. So typically the calibration, the internal calibration of the camera is done by the manufacturer, and we don't concern about that. Okay, then if we are moving back to the, okay, just to this C, okay, that in the end is telling us about the position of the camera in the world coordinate frame. So is the centrum of the projection. And also the ER1, ER2, ER3, that in the end is telling us about the relative rotation of that centrum. Okay, is the coordinate system of the camera. So those two, C and R, are the external camera parameters. Well, in the end, are external to the camera. The camera is moving in the world coordinate system, and obviously we'll just have different position in that system. And if we are just rotating, we'll just have different rotations of the camera coordinate system. Okay, so those are external camera parameters. So now we have internal parameters, and are those that are here, and we have external parameters that are in the end external to the camera. Okay, so if we know both, if we know the external parameters, we know that the camera is externally calibrated. We know how it's placed in the world coordinate system, and also we know the rotation of it. Okay, so fully calibrated means that we know both the internal and the external parameters. So we have both internal and external calibration of the camera. Okay. Now, often we are using homogeneous coordinates to linearize some nonlinear relations. So basically, we are adding something like this. If we have X and Y, we are adding some extra homogeneous. Okay, and we are ending up with this kind of homogeneous coordinates that is just adding some flexibility by adding extra dimension. Okay, and this is pretty much a simplified way of saying that homogeneous coordinates are only defined up to a factor, and that factor in the end is coming from the extra dimension added to the coordinates here. Okay, so for 2D, typically we are relaxing and going in homogeneous coordinates and add a third one. For 3D, we are adding a fourth one, and we end up with this kind of homogeneous coordinates. Now, if we are looking at projection matrices, and we have the U and V in the image plane, we have the focal distance, we have the rotation matrix of the camera, we have the placement of the camera, the centrum, where is the projection. Okay, and we have the X, Y, and Z coordinates of the object in the world coordinate system. Now, exploiting the homogeneous coordinates, we can just write the same thing using this. Okay, so we are still identifying here U and V. Okay, this third dimension is coming from the homogeneous coordinates. Okay, and then we are identifying here that we have the R values from the rotation matrix, F from the focal, from the length. Okay, we have X, Y, and Z, the world coordinates, and the C1, C3, C2, C3 that are in the end the coordinates of the center of projection where the camera is placed. Okay, so this is a different way of writing the projection matrix, okay, using homogeneous coordinates. So you can just take a pen and a pencil and see what happens there. Okay, now if we are looking also at the image pixel coordinates, okay, we have the relationship between pixel coordinates X and Y to the U and V. And U and V, we said what is here. And now, if we are just writing down, we just have this written like this. We are adding the extra dimension from the homogeneous coordinates, and we can end up with this formulation where we are getting the internal calibration parameters, the internal camera parameters, okay, placed here, all the 5 of them. And we have here the homogeneous coordinates of the image plane, the one that we had here. Okay, so basically the pixel coordinates will be a multiplication of this matrix that contains the internal parameters of the camera and the homogeneous coordinates of the image plane where we are forming the image. Okay, so this is, and then we can just summarize and see that, okay, this is the image plane coordinates, homogeneous coordinates, and this is the pixel coordinates in the image. Now, if we are just concatenating, so we are showing the image pixel coordinates as being the matrix with the internal parameters times the U and V homogeneous coordinates. Okay, we are ending up with that, and now we can even separate the F from the rotation matrix. We are ending up with this. So rearranging, we are having this. So pixel coordinates in the image plane, we have the internal parameters, we have the focal, we have the rotation, and we have the X, Y, Z, and the centrum of the projection, the centrum of the camera. And now, if we are just placing those two, we are having a calibration matrix. This. That is just the internal parameters and F. And yeah, we can just write them in this form. So now we can define a P in a homogeneous coordinates in this form. So we have pixel homogeneous coordinates, the point in the world coordinate, and the homogeneous coordinates in that world coordinate. So now we can just write down in such a manner, okay, where we have the calibration matrix, the rotation matrix from here, and the point minus the centrum of the camera. Okay. So this is different ways of writing the same stuff. So the P equal with those. Okay, so what we have here is just different ways of writing the same projection matrices that are lending to pixel coordinates. So we have pixel coordinates, homogeneous pixel coordinates, and these are different ways of writing the same thing, this. Okay. So this is what means projection matrices, and going from, yeah. Okay. Going from a camera that is placed somewhere here in a world coordinate system that can be arbitrarily picked. And we have some points that are defined according to this, but we need to go through the camera, and in the camera we have an image plane and rotation and position of the camera. So the rotation and position of the camera are external parameters, and the internal parameters are those that are defining in the end the pixel coordinates, how actually the image is formed, the image is formed in the sensors are formed on the camera. Okay, so we need this kind of parameters in order to control the projection and everything that happens on the camera. Okay, so now a bit about object gradients, pixel gray levels. So probably I will not enter too much. Probably I will even skip this part. So here is just a simple formula that typically was applied nowadays. Is not so much on digital cameras to correct so-called gamma correction of the images. So given an image with some values in each pixel, okay, we were applying some sort of gamma correction. So lifting all the values to some power, a gamma, okay, and adding some gain multiplication and some addition to some dark reference. So what means having nothing, no light. Okay, but nowadays most of the digital cameras are having a gamma equal with 1, so we don't need to correct. And the dark reference and the gain are also quite well behaved. Dark reference 0, gain 1, and that's it. Okay. Good. So this was about the acquisition of the images. And now we'll go to the surface features, color and texture. Okay, so when it's coming to objects, it's quite clear. We have some surface, and that surface in the end is defined by color and is defined by some texture. That texture in the end is a matter of the geometry, but also is a matter of whatever the patterns, color patterns might happen there. Okay, so a bit of discussion here. Color. I will give a little bit of overview of color spaces and what we can expect from this side, and then we'll see a little bit about texture. So first, color. As mentioned before, we are focusing on the visible spectrum. Typically is considered somewhere between 400 and 700 nanometers wavelengths. And yeah, we have a perception of the brightness, and this perception of the brightness relates to the saturation of color or the wavelengths that are forming the light. Okay. So I will simplify here. So we have a link between radiometry and photometry. If you are just looking at what means radiometry, we have radio and metry, and photometry, photo and metry. Okay, so directly from the naming, the photometry is dealing with some measurements of the photo. Photography in the end has a subjective feeling, because a photo is meant for interpretation by humans. Okay, so is subjective in the end, and photometry typically is referring to subjective impressions and measurements. While the radiometry, if we are taking the radio and metry, okay, is handling radio wavelengths, radio like physical properties. Okay, and typically we are just making this distinction. Radiometry is referring to measurements that are involving physical and objective measurements, and photometry, we have subjective impressions, and relates closer to the interpretation, human interpretation. Okay, so something else here. Yeah, we have a relationship. Typically, the brightness and so on, we can measure like lumens using lumen, and divide over watts and so on. Anyway, so I'm not entering this. The study of color. So typically, we are using the color to please our eyes, and we need to visualize the results, the visual results. We are interested in using the colors to characterize objects, and not only. And in this way, we are extracting some sort of color features, okay, and are meaningful for a recognition task, for example. Also, the color and the study of color is important for generating colors. We need to generate colors or to render color for displays. We are looking at some screen at the moment, okay, and we need also to use some light, for example, for inspection. And we studied the color to understand also the human vision. Okay, so if we are looking at the perceptual attributes of light in a human sense, so typically we are distinguishing brightness, hue, and saturation. And here is a depiction of those three, let's say, components for light. So on one side we have white and we have black. So if we have black, this means absence of wavelengths, absence of everything. If we have white, or pure white, then this means a combination of all the wavelengths. Okay. So, and then we have a connecting line there that is going from black to white. This means that actually we are having an increased presence of wavelengths. Okay, in the end, if we are saying that we have wavelengths, we have electromagnetic waves, and the electromagnetic wave, you know that in the end is like the light and so on. In the end, we are speaking also, if it's to speak about corpuscles or particles, we are speaking about photons. Okay, so on this relationship between black and white actually means that we are getting an increased amount of photons or an increased amount of presence of wavelengths. Okay, that is connected from black to white. Good. Now, at some point, if we are staying only on this direction between black and white, and everything is not well differentiated in terms of hue and saturation, so it's not very saturated in color domain. So hue, in the end, tells something about the wavelength. So at the extreme, if we have a saturated hue, then we can just connect directly to the wavelength in the visible spectrum. So we have pure spectral colors that are residing here on this circle. And these pure spectral colors, yes, we can say here is a red, here is a blue, here is a green, whatever. And at the extreme, we have the extreme saturation and everything is fine. If it's something that is unclear and is combined and something in between, then actually we have a mixture, and that mixture in the end is leading to something that doesn't exhibit sufficient hueness. Okay, and this and saturation of color. And what I'm trying here to say is that whatever is here is in the middle and aligned to the black and white direction is pretty much a line of grays. So it's a gray area. So the wavelengths are there, is a combination of them. There's no wavelength that is taking the lead. So we don't get a chroma. Okay, so this is like a representation about the space of wavelengths in the visible spectrum and what we are perceiving as attributes of light as humans. We are perceiving a brightness, and is going from black to white. We have a strong direction between black and white for everything that doesn't concern necessarily color. And then when it's coming to the chroma, we are perceiving some hue, and this hue is connected to the visible spectrum colors, so from blue to red, okay, and some sort of intensity or saturation in the color is just connecting to the individual presence of each wavelength in separation. Okay, so this kind of color spaces, okay, are many color spaces. CIE is a standard organization for colors, and yeah, if we are perceiving the color something like this, we are having a hue, a saturation, and a luminance or brightness, okay. And when we are looking at the disk of chroma, okay, we are getting this kind of partitioning, and we are just assigning some naming to the colors, okay. The standards, yeah, are defined there, and some of them are more used than others. Okay, so in the history of color, Newton was proposing the spectrum and analysis. Jung came to the three stimulus model, so RGB. And then later, after this three stimulus model was pretty much taken for real, okay, later we were realizing that really we have three cone types, and these specialized photoreceptors in our retina and so on are aligning also to the RGB, to the three stimulus model. Okay, so the retinal cones are in the end somewhere around 400 something and at 500 and something. So those are the peaks of the three cones, types of cones, and their peak sensitivity to the wavelengths. Well, we are getting these raw readings in our three types of cones, and then our brain is making the rest by combining and creating intermediary colors and finalizing the image we are perceiving with our eyes. Okay. So I'm not entering too much on those. What is important to know? Yeah. So yeah, about 10% of population have abnormal color vision. So daltonism. So some are not perceiving some colors or distinguishing between some colors. Okay, some birds are having 4 cone types, are extending into the ultraviolet range. Okay. So I will go fast because we'll not, in this course, will not focus too much on the color and color properties and okay, and neither too much on the standards. Okay, so what is important to know is, yeah, are multiple standards. The color and the color spaces are not uniform, and the geometry or the Euclidean distances, as happen in a geometrical real space and so on, are not meaningful in a color space. So in a different way of saying, what we are perceiving as distance between two colors is difficult to project for a distance between other two colors or to do any sort of mathematics with colors. So we have some smoothness in the colors, but that's it. And on something else that is important. So the standards and the standards used for representation of images and display and so on are in the end defined in such a way that are normalizing the channels, the red, the blue, the green. So an image, and a digital image is formed or is represented by red, green, and blue readings. Okay, so it's a 3-channel image. Okay, and typically these values are normalized in some range, 0 to 1 or 0 to 155. Okay, that is giving some representation of the color channel. And yeah, there are all kinds of transformations between different color spaces. And for example, there are also some 2D projections, like for example here, the CIE XY color triangle. So basically B, R, and G stands for blue, red, and green. Here are the values on X and Y projection. And everything that means visible spectrum is supposed to be included in this area. And B, red, and green at the boundary is like the point of the highest saturation of that hue value. Okay. And all the wavelengths or the color is supposed to be in this space. However, if we are doing some small distance between two colors here, that kind of small distance might have a totally different meaning between two colors somewhere else in this area. So here is more visible. So as mentioned, here was a blue, here is a red, and here is a green. So our conventional naming and so on, that is connected to some wavelengths and is quite clear. However, we are more sensitive to some changes in green that are connected also to the grayscale and luminance, okay, and less sensitive to what happens in the blue. or even to the red. And whatever happens here not necessarily will be subjectively equal with what happens here. Even if you are projecting this space, yeah, you are getting some distances, geometrical distances, those will have totally different meanings. Because, yeah, you cannot do mathematics with colors. Not yet. Okay, so they're also called primaries, or basic reference colors for red, green, and blue. And those are depending on the standards. So this is, and this kind of depiction is quite standard. Here is what I was mentioning. So if we are looking at some smoothness and local consistency in this space of colors, then we may consider that these ellipses are including some colors that are having comparable, let's say, for the standard deviation of the colors in those ellipses, okay, is the same in all those ellipses. But we are saying here that, for example, here for blue, we are getting a very small ellipse. This means that there are a lot of changes in a small part of this space, okay, while here we are seeing a huge ellipse, okay. So somehow we see that the space is allocating much more space or values for the green than for the blue, and so on. So the distance in this triangle is not a faithful indication of perceptual distance, what we are perceiving as different. Okay. So I will move on. So in the end, the color of a surface is the result of the product of spectral reflectance and spectral light source composition. So in the end, we have the light source that is coming with some wavelengths, and we have our reflectance of the surface, okay, and that depends obviously on the material and on the particles that are forming that object, or what is on the other side of the surface. Okay, and the color in the end is the result of incoming wavelengths interacting with the material. So what we discussed before about the interaction of the light with material. Okay, our visual system can okay. We are quite how to call it, tuned with to our environment, and in the end, we can tolerate also different light sources and some other changes, and still disambiguate between the effects that are produced by the light source and what is coming from the surface. Okay, the color of the light source can be guessed via that of specular reflections, but the visual system does not critically depend on this trick. Okay, so somehow we can figure out if the light source has some bias. So if it's a white light, or if it's a reddish light, or a bluish light, and so on. And yeah, this is something that we just are able to do that. But we need to pay attention when it's coming to the computer vision algorithm and the interpretation of the visual data. Well, we are not equipped with the human visual system, and we just need to pay attention at normalizing and the effect of the illumination on the images. Okay. So invariant color features and the illumination invariant color features are very important. So already mentioned here, if you are using a light source that is reddish, you'll see everything in reddish. So if we want to compare or recognize objects or do whatever, then it's very important to be able to get illumination invariant color features. So extracting the true surface color under varying illumination, as we can do it to some extent, is very difficult. Less ambitious is to extract colors do not change with illumination. And here we are just making a list of changes. We have spectral or internal changes, geometric or external changes, and combination of spectral and geometric changes. So if we are speaking about spectral, we are referring to the spectrum, electromagnetic wavelengths, the visible spectrum eventually, and the internal changes, because in the end those are supposed to be innate to the properties of the material. Okay, then when we are referring to the geometric, is pretty much about the shape and the way is bounded, the boundaries of the material. Okay, and typically are considered external because you can have deformations, and those deformations are not necessarily changing the properties of the material, are not changing the colors, but will change the geometry of the surface. Okay, and then are the combination of those two. Okay, so if we are looking at illumination invariant color features, the spectral changes, yeah, we can just check for materials and see if actually are changing depending on the illumination. I'm not entering here in what means those inspection and how to evaluate. For the geometric changes, again, we can just try to see for different illuminations if the geometry is changing for those different illumination or different lights. Okay, and we can just determine some invariants with respect to RGB and the combination of them and so on. Okay, I'm not entering the details. Here we are getting again back to the ideal conditions. Ideally, for any surface, in order to predict what happens with that surface, given any sort of illumination, we will need in each point on that surface, okay, to know something like this, to know the normal and to know this set of parameters. Okay, that are telling us pretty much how for each wavelength or for each incident ray, the reflection will behave. So, and this for all the wavelengths. Okay, so this is like a ideal goal, and it's quite difficult to achieve. Okay, in controlled settings, we can just get some estimates and register pretty much some objects and determine for those objects some approximated such functions. And then, yeah, if we are getting something to learn from, then we can have some real, if we are applying some light sources and we are seeing the result of that light, okay, and some simulated, if actually our model holds, and we can just see if our predictions are comparable with the real thing. Okay, so this is like a holy grail because, yeah, will just give us the power of controlling and knowing how actually the surface behaves with different lights. But typically we don't have this luxury. Okay, now discussing about texture. The texture in the end boils down to the patterns or the changes in color and ages that we can see for different objects or for different materials. Okay, so here are just a couple of textures. Some of them are natural. We just look at the clouds, where we are looking at this simple materials. Okay, some other are just human painting or whatever. Okay, so basically we can say something about this kind of texture. We can have some oriented, some patterns that are repeated and are oriented along some directions. And we can have something that is not oriented or has the same kind of properties for different orientations in space. We can have regular, so we have a pattern, and this pattern is repeating with some regularity in the area with the texture, or we can have a stochastic, it just randomly appears similar patterns. Okay, we can have a coarse, so at some size or scale level, we are getting some pattern that is visible, or we can have something that is more fine, something that is more regular at small scales. Okay, so in order to characterize the features, the textures, okay, we can use a number of tools. One is Fourier features. Another one is co-occurrence matrices. Then filter banks, and none on the list, the stochastic models. Okay, so let's take each of them and briefly see what it's about. First, the Fourier features. So basically, the Fourier features are based on the Fourier transform and are based on the integration of regions of the Fourier power spectrum. Now, I won't be able to cover Fourier transform and Fourier space and the operations there. And this is also not critical for this course, and you'll not have the Fourier transform as an exam topic. If you are very interested in so on, it's quite basic to understand what means a Fourier transform and how to apply a Fourier transform to an image or some data. And yeah, a Fourier transform is a quite powerful technique, and it gives us a very useful information in the frequency domain. Okay, so I will jump over most of the slides that are dealing with Fourier, and yeah, feel free to learn by yourself. Then we have co-occurrence matrices, and what means this? So if we are looking at an image, this means a grid, rows and columns, and over this grid we have a number of pixels. Each pixel in the end is just a value. If it's an intensity or grayscale image, then we just have a value, and it just tells us the intensity in that pixel. Or if it's an RGB image, then this means that the image has 3 channels, and we are getting 3 values, one for red, one for green, and one for blue. So having this in mind, then we understand that the image, we can just see it pixel level, or we can see it like a whole. the relationship of all the pixels that are giving us the high level understanding of the image. Okay. So if we are handling a set of pixels, okay, and we are just removing the position of the pixels in the image, then we can still get some statistics. We can create histograms of the values and so on. So histogram in the end is telling us just a summary of the values, okay, and what is in our image. And disregards the positions. So for example, here is an example of a histogram. Sorry about the low resolution. So this is a histogram. Here starts at 0 and here ends at 255. This is the axis that is meant for the value between 0 and 255, the 256 levels of a gray pixel in a gray image. And now if actually we are just taking from the image and we are counting how many pixels are of this value, let's say 200 or 255 and so on, we are getting some counts for each of the values from 0 to 255. After we are getting those counts, we can divide the whole thing and normalize such that to get a histogram that is displayed here. So here is a normalization such that on the y-axis here, we have from 0 to 1. So this means that we just got the count and then we took the maximum, probably around this value, maybe 90 something, okay? And this maximum value that was here was used to divide all the other values. So this is like a reference, is the maximum, let's say, or the value that appears the most often in this image. Okay, and everything else is becoming relative to that, something between 0 and 1. Okay, so this is just giving us a visualization of what happens at the level of values in the image without actually paying attention at the position of all the pixels. So it's just a summary. So this is what means a histogram in the end. It's just a historization in a number of bins of what happens in the original data by dropping quite a number of aspects like the 2D position here and the counts, the number of pixels. Okay, so when we are saying the co-occurrence matrix, so basically it's a similar thing like here, only instead of dropping entirely the position in the image, we are saying something else. Instead of looking only for the value, actually we are looking for pairs. So we are looking for pairs of values. And it's not only pairs of values, but pairs of values with some relationship. So we are looking, for example, if we are taking 2 pixels that are 5 pixels away. Okay. These 2 pixels that are 5 pixels away, we have the geometric relationship between them. Okay, like here, we just say we have 2 pixels and those are supposed to be in some relationship. 3 pixels on the y and 5 pixels on the j pixel coordinates. Okay, and this relationship is just imposed to the image and we are just extracting from the image, from all the positions, such pairs. And then we are just keeping a 2D statistic matrix Okay, and we are just getting for each paired intensity I and j, we are just counting how many times this paired intensity I and j happened in this geometrical relationship in the image. So if we are doing in this way, we are just generating the so-called co-occurrence given a geometrical relationship. And after getting this co-occurrence, we can just look at these frequencies, and we can just do the same kind of normalization like here, or visualization. So just to be more understood, we have the original image, and we are assuming that this is the relationship. So we have the extreme points of this segment. We are just getting this segment moved in all the positions, in starting positions in this image. And for each placement, we will get two intensities in the extreme points. And then in this histogram or co-occurrence matrix, we are just having for one intensity and another intensity. So basically from 0 to 255, 0 to 155, okay, we just placed there and counted how many times we found this particular pair of intensities as extreme points of this segment. Okay, so we are doing this kind of frequency counting, and here we are just reporting the matrix after doing some normalization between 0 and 1 or something like this. Okay, so this is another way of characterizing a texture. So we have something like this, and we are disregarding everything, and we are just looking at pixel intensity, and we are getting an 1D signal and normalize it. That is just a histogram. And here we are getting like a generalization of that, where we have a relationship between two extreme points and get a 2D co-occurrence matrix. Okay. Now, if we are starting from that kind of co-occurrence matrix, and we are considering that this is C, okay, then based on the values in that matrix, we can compute this kind of sums or expressions. And we can, based on these sums, we are ending up with some values. And these values, in the end, we can give them some names. And these names are meaningful for the image that we are analyzing. And yeah, if you know a bit from whatever, information theory or from physics and so on, so typically the energy is a power of 2. The entropy is a, let's say, P log P, okay? Contrast is something that places some difference, okay? Homogeneity and so on, how is defined, and the maximum probability, that is just a max over the whole thing. Okay, so those are some way of extracting numerical feature or characterization of an image. And in the end, this number many times is quite well connected to what is the original image, and can help to distinguish between textures. Okay, so this was about histograms, co-occurrence, and then filter banks. So here are some basic filters, and those filters were Lowe's filters, were defined some, I think, 50 years ago. Okay, and were very useful in very constrained scenarios. Are defined like 1D filter. What means this? So we have like a vector or a mask of some weights, and then if we are going to some image like this one, we are just applying that mask, okay, and compute some scalar product between that mask and the original values in the image, and end up with some values. Well, if it's a scalar product, we are ending up with one value. So basically, if we are sliding such mask or filter over an image, we are replacing each time we slide it and shift it to the right or down by 1 pixel, we are replacing with the result of the scalar product between the filter and the original values in the image. Okay, we are ending up with a image result. Okay, that is the result of applying that filter. Okay, so we can get in this way some so-called filtered images. And these filtered images is just telling us some story. So for example, this filter here is containing something with minus, something with plus, and centers in 0. So if you are ignoring some middle value and try to balance the extremes, it's just giving you some information. Or is just emphasizing something in the middle with respect to the surroundings. And pretty much this is just emphasizes if you have some pixel edge in the image.
All these filters are just 1D filters, but normally we use 2D filters, right?
Exactly. Well, here for the sake of completion, I'm pretty much reviewing also these Lowe's filters that were introduced some 56 years ago and are the basic filters. Nowadays, and especially with convolutional neural networks and so on, we are applying mostly 2D filters. And those 2D filters typically are learned, and we see them like kernels or convolution matrices. Okay, we'll get back also to the convolutions and so on once we are getting there. But yes, those are only 1D filters, only applied on one direction. We can also transpose the whole image or the filter itself and apply it on the other direction of the image. What is important in the end is that all those filters are capturing and are ending up in providing some description that can be useful or not at describing some textures. So this fixed filter set yields simple convolutions, but has proven very effective in some cases, especially in controlled environments. And yeah, when we do not have too much learning involved. Then there are some other filters, and this is part of the 2D filters in a sense, but we can define also 1D filters, like Gabor filters and some other filters that are, or Gaussian filters that are having a 2D support. Okay, so if we are looking at a Gabor filter, typically it's defined something like this. So we have X and Y coordinates and some expression. I'm not entering again, I'm just keeping the power and the discussion in the frequency domain. What is important is that in the end, we are having some filters that are applied with some 2D support, so are matrices in the end. The filters are still containing, like here, so some set of weights. And when are applied to the image, we are simply applying a simple scalar product between the 2D support filter, okay, and the image at each location in the image, okay. And if we are doing it in this way and are applying some filter that, let's say, responses to horizontal structures, okay, we may get this kind of response image. So this means that for each value here, we applied a filter in the original image, and then we shifted 1 pixel, applied again, and get some other result of applying that filter. This means a scalar product between a mask 2D matrix and the original image values. And we are ending up with something like this. So already by looking at this image, we see that whatever is that 2D filter may create this kind of images where we can see easier some, let's say, horizontal or some vertical structures. Okay, so this is the whole idea of the filters, just emphasizing some properties that are happening in the image. Okay, then are so-called eigenfilters. So, for example, here, filters adapted to the texture, and we have just a simple procedure to extract and to learn such filters. We are just getting some mask. We are just shifting this one over the image, like this. And by shifting this mask over the training image, we are just getting a lot of statistics, a lot of such small masks that are there. Then if we are getting all those masks placed together, so you can just imagine that you are getting some small crops here of a fixed size. Then if we are just getting all of those and we are applying something like PCA, this means principal component analysis. Well, this is supposed to be like a basic technique, but in the end, well, I will provide you also some slides, and probably you'll need also to learn yourself about the PCA. In the end, it's just leading to the principal components or a basis that is aligned to the major variation directions in the space of these cropped small images. Okay, so if we are doing that, we are extracting like a basis in that space. We are getting some directions in that space, and these directions in the end can form our eigenfilters. And then these eigenfilters and the result of applying this PCA could be used directly to create some filters that are then applied to the original image. Okay, so this is a very simple way of learning some meaningful filters that are adapted to the texture. Okay, so anyway, here is just some example textile inspection. So obviously, if we are learning something from small patches, we are learning the most common pattern. And then if we are applying the most common pattern, obviously whatever is different will just create some sort of response that will stand out. So yeah, this is why it could be quite useful for textile inspection. So we are getting some materials and we can spot the differences. Okay, so this is a little bit going into details. I will just skip. It's just what means this kind of eigenfilter. In this example, could be something like this: 17 times 13 pixels, and or something like this. We are just getting some covariance matrix for the PCA when we are computing weights, and we are getting some filters. Okay, and yeah, if we are applying those 9 filters like this to the original material, we may get this kind of results. Some of those results are emphasizing exactly this defect that appears at least in 3, 4, 5 filters, quite obvious. Okay, and we can look at the result of the filters or some energy, so power 2, something like this. Okay, anyway, so this is a type of capturing some texture information, and is an example of how to apply it, let's say, for defects in a textile and materials. Okay, so this was a little bit about texture and some ways of characterizing texture. Now is 2 o'clock. I will propose to continue another half an hour and then to end our lecture instead of taking like 10-15 minutes now break and continue for another half an hour or something. So what do you think? Is okay?
Yes, sure.
Okay, let's do like that.
Yeah.
So now let's move to the sampling and quantization and image enhancement. So, okay, so initially these slides were defined mainly for analysis in the frequency domain with Fourier transform and so on. Since I mentioned that will not be the time and also will focus more on deep learning at some point and some other techniques in this course, I will just skip part of the frequency domain analysis. So let's look back at the cameras. So we have CMOS technology, complementary metal oxide semiconductor, the most used technology at the moment for the cameras. And we know that the cameras, the digital cameras, are producing images on a 2D grid with a number of pixels. Okay, so when it's coming at image representation and working with images on a computer, typically we are with some discretization. And the computer is processing an image by doing a sampling. So basically, very few times we are working with the original innate resolution of the sensor. So most of the digital cameras, especially the smartphones, are having a huge number of pixels, but the final images are in much lower resolution. Well, this is coming from the technology itself. More pixels allows more observations, but also are noisy, so you cannot rely on those pixel observations, and then you just need to combine them, and if you are combining them, you are reducing the number of pixels. Okay, so on one side we have a sampling, we are reducing the number of pixels, and on the other side we have a quantization process. So sampling is referring to pixels and reducing the amount of them, or like this. And quantization typically is referring to the number of levels we are working with in representing the value in each pixel. So if we have a gray image, we are just working with intensities. Quantization will refer to the number of gray levels. Okay, so if we are looking at a gray image like this, and we are getting a very small crop like that, then if we are looking in a even smaller area, okay, directly at what means the image, basically the image means one matrix, a 2D matrix, and in each pixel in the image, we have actually a number. And this number or value is some value between 0 and 255 if the original image is so-called 8-bit or 1 byte grayscale image. So we are allocating basically 256 levels to represent what is the gray value or the intensity level in each pixel in this image. Okay, so a grayscale image is just a 2D matrix, and each cell in each corresponding pixel, we just keep a value, and that value is typically a level between 0 and 255. Okay, so this is the basic. If we have an RGB image, basically we have three such matrices. So it's a 3-channel image or 3 times this 2D matrix, and each channel will just contain similar values for each of the 3 color channels. So you'll have something like this for red, for blue, for green. So, and then the rendering and so on will just place together those 3 values to form the combination, the color combination that we are perceiving. Okay. So now when it's coming to the sampling, yeah, there are many ways of doing a sampling of a high resolution into some lower resolution. And regular image covering tessellation could lead to 11 such tessellations with regular polygons, but only 3 are equal. So here are 3 examples of covering an image with some patterns of equal size. Okay, so we have the standard grid, the square, and the most common. Then we have some triangles, equilateral triangles. Okay, and we have a hexagonal representation. So if we are looking at those 3, what we have in most of our technology, and is the most popular decision and use, is the rectangular or square pattern used for representing the image and also for sampling over the image. Okay, however, out of those 3, the best will be, from a point of view of theory, and not only, is the hexagonal one, because then actually all the neighbors of one are at equal distance and in the same position. Okay, so it's more isotropic, no connectivity ambiguities. There is a similar structure with actually what happens in our retina, in the human eye. Okay, but this might pose some issues when we are dealing with our computer written algorithms, because yeah, we are just structuring almost everything in rows and columns and some sort of accessing of the information. But yeah, this is what is standard. It's just a rectangular square representation, and it's good for you to know that there are other ways of doing this. So here is an example of sampling. If we are starting from this image, and then we are just sampling over a grid using this kind of pattern, like here. So basically, we are just sampling each second pixel. Okay, we are ending up with this image. And then we are applying the same and the same. We are lowering the number of pixels in the image to this. So this is the effect that we can perceive on the image when we are sampling down the number of pixels. So all of those are representations of the same contents. The biggest difference is that one is giving us more information, rich information, while the other are just less information, to the point where we don't find very useful. Okay, now if we are doing quantization, as mentioned before, refers to the representation or the number of levels we are considering in each pixel. So if we are in the same setting, the original image was using 256 levels, grayscale levels, values from 0 to 255. And this means that in the picture, in the image, we were allocating 8 bits or 1 byte for each pixel in the image. Okay, now if we are reducing and we are just doing a simple reduction from 256 levels to only 8 levels and just uniformly distribute the values, okay, then we are getting this image. Still, most of the details are preserved and we can still make quite a bit of use of what is in the image. However, if we are going to 4 levels, already we are seeing something that looks more, looks artificial. Are only 4 levels and we cannot distinguish much, only the main geometry. And in a even lower level, if we are using only 2 levels, basically we have a binary image. In each pixel we have 0 or 1, so everything or nothing. We are still getting some idea about the major structures in the image, but most of the information is lost. Okay, so those are examples of sampling and quantization. And yeah, here is some other example. If we are starting with this and we are reducing by sampling, so we are reducing the number of pixels, at some point is useless, the representation. Or if we are doing quantization and we are ending up something like this. Okay, so binary images or 1-bit quantization. So if we are keeping only 0 or 1 in each pixel, this can be useful in some industrial applications where the memory is quite expensive. However, the non-uniform sampling and or quantization could help to keep details and to adapt to the local structures. Okay, so here I'm just mentioning some simple sampling models. So we can integrate brightness over some cell window, and we can deal with some image degradations. And we can read out values only out of the pixel centers. And this can handle aliasing or leakage as problems that are typically found in the images. Okay, so if we are integrating over some pixel cell, okay, simply means we domain like written here for okay, using a convolution and then the integration and so on. So basically boils down to computing some average over some area, okay, and yeah, this is just a depiction of what means to convolve over some area. If we are computing just integration and is just uniform weighing, we are just averaging the values, then that convolution mask that is there will have just equal weights, non-zero equal weights, and then we are just ending up with a summation of the values that are in the red square. Okay, so if we are doing this way, we are just computing an average or a sum in that part. We are taking an average if we are dividing by the number of pixels that are covered by the mask. Okay, so I'm not entering in the convolutions in the frequency domain, Fourier transform, but yeah, simply said, we can integrate over a cell window. The simplest thing, we are just computing some local average. Well, there are some other more interesting ways to do it in frequency domain using Fourier and so on. And I'm just skipping those things. Okay. Okay, and then is the reading out values only at the pixel centers. And this is helpful to deal with aliasing and leakage. So again, in the frequency domain or in integral or using Fourier transform and so on is more principled. But anyway, you could just imagine that the intention is to pick something that is more stable and alleviate as much as possible the creation of artifacts. So if we have a high resolution image and we are just downsampling, this means to pick up some values from the original set of values, so some pixels from the original set of pixels that are more stable and representative for the original set of pixels. So in a different way of saying, if actually we are having, for example, 3 times 3 pixels in the original image, and those 3 times 3 pixels in the original images are just values of 100, and in the middle of this 3 times 3 is one value of 89 or something like this. So it's something that is different than the other 9. Makes more sense to, and we are doing a downsampling by a factor of 2. It makes more sense to replace this 3 times 3 not with the middle central pixel that is there, but with something that represents better what happens in that 3 times 3 cell or sub-window or patch. Okay, so then you could just get the median value or some average or something else that actually leads to something that is more or closer to the underlying signal of the image. Okay, so this is just like a simple insight about what exactly happens there. Okay, now if we are looking back to the discretization, we have sampling and quantization, sampling of pixels, quantization of gray levels. And if we are looking at quantization, here is a simple case scenario. We create k intervals in the range of possible intensities measured in bits. So if we have 256 intervals, then that log 2 from 256 will just be 8. So we have 8 bits for 256. Okay, now if actually we have only, I don't know, 16 intervals, then this means that we have only 4 bits. Now, this is one way of creating a quantized representation in k intervals or for k levels. So we have some design choices and some decision levels. If we are defining, like here, we have k plus 1 decision levels. We are taking some representative values in each interval. And then we have a selection procedure. We can do equal intervals. Value is the mean in each interval. And we can use some uniform quantity. Okay, so basically, if we are taking some image, like we have seen before, that is grayscale and has values between 0 and 255, okay, then, and we want just to reduce, quantize to, I don't know, only 4 or 8 levels, okay, then for these 8 levels, we just have a mapping of the original 0 to 255 needs to be mapped to the 0 to 7, such that we have only 8 levels. So in order to do that mapping, okay, we just need to see the kind of intervals. So now we'll have only 8 levels. We have only 8 intervals, okay, and these intervals needs to be representative for the original image, and each such interval will just end up or will land only with one level in the 8-level representation or quantized representation. Okay, so the simplest thing is we are just dividing equally 256 divided by 8 and to get some range intervals, and everything that in the original image corresponds to those intervals will just be translated to the index of the interval and will be an index between 0 and 7. So that is the easiest. Other forms will just assume that we are adapting to the information in the image, and we can just cluster the pixels in the original image. So if we are clustering them, or if we are getting a histogram, we are just seeing what pixels are appearing more often and allocate more bits or more levels for those pixels and less for the other. So in this way, we are preserving more information from the original image. Okay, so are quite a number of ways of doing. So here is the example of uniform quantizer. So basically, we are just taking the original interval, divide in the number of intervals that we are requiring, and then everything that gets in those ranges will just be mapped to the new levels in the quantized scheme. Okay, so here is some example. We have a 256 gray level, 8-bit, and we are moving to a 11 gray level. And yeah, already we are seeing quite a loss of information. And is an example of under quantization because we are losing information. It is quite visible. So typically in the images, we are getting 8 bits per pixel, and the grayscale image or the 8-bit pixel image is we call it monochrome. Is only one channel, and also it's quite often that the RGB images or the color images are the 3 colors or 3-channel image. And for each channel, we are getting like 8 bits. So it's like 3 times the monochrome setting. However, there are quite a number of other images and standards, like medical images, or that can go up to 16-bit or even more. And also the modern, new, expensive cameras are also representing the data on more levels. At least the original sensors and the raw images are like that. Okay, so this was about quantization, sampling, and now let's look at the image enhancement. So there are 3 types of image enhancement that we'll discuss a bit more in this slides. Okay, we have noise suppression, image deblurring, and contrast enhancement. So given some original image, for example, the one here, a noisy image looks like that, a blur image, and a bad contrast. So all those 3, noise, blur, and bad contrast, are very plausible images that often we are receiving from some cameras or tools. So rarely we are getting a clean, good quality image. So this is, we call it original, but it's more like an ideal image or ground truth. And in reality, typically we are getting what we are seeing here. Images affected by noise, blur, bad contrast, combination of such problems. And yeah, when it's coming to the noise, typically we are assuming that there are some pixel-wise noise. So what means this? Means that instead of being the original level or the ideal level in each pixel, we are getting some value that deviates from that ideal case by some amount. If those deviations and so on are following some distribution, for example, a Gaussian distribution, and this Gaussian distribution is well behaved, we have a mean and standard deviation, then we know the kind of noise is a Gaussian noise, and each pixel is affected by such noise. This is quite important. If we know the distribution of the noise, we can devise some models that can, in the end, help us to remove the noise or to diminish the noise in the image. Also for the blur, in the blur case, instead of getting something like the original or the ideal value that is supposed to be there, we are getting a value that is the result of some combination of the immediate pixel values. So immediate, meaning in the local neighborhood, the neighboring pixels are values are combined to get the value that is in the blurred image. If this blur effect is the same or follows a similar behavior in all the parts of the image, then we are getting a uniform blur kernel that is at the whole image. And this is like the easiest and the best we can hope. And then if actually we can figure out the kind of blur that's applied there, then we could aim at deblurring or removing that blur. Okay, then when it's coming to the contrast, pretty much means that instead of showing nicely from 0 to 256 levels and as much as possible uniformly, uniformly in the relationship with the frequency of the pixel values that are in the image. So we're getting a good spread of the values. We are getting like a skewed distribution. So most of the values will just go either to white or to the black. The ends are still there, but are difficult to visualize because we are less sensitive at small differences. So from our point of view, from our eyes and so on, it's better to have a better equally spread set of values, intensity values in this case, okay, done to get all of them shifted in one side of the representation interval. So if we have 0 to 255, do not get most of the values at the extremes, let's say, either to the white or to the black, okay, and nothing in between. So that's why here we have a bad contrast. Okay. So I will skip again the Fourier story and so on, even if it's much more interesting to handle the data in Fourier or in frequency domain. Okay, so we have a noisy observation, we have an original, and yeah, we have quite a number of ways of reducing the noise or suppressing the noise. So here are consider like two general options. One is a linear filter or convolutional or low pass convolutional filter, and the other one is a non-linear filter. Okay, and especially median and anisotropic diffusion. So in a low pass filter, okay, I'm not entering the Fourier. Okay, so I will just go more into the straight implementations. So one of the most straightforward convolutional filters are average filters. So this means we are just getting a mask, let's say 3 times 3 or 5 times 5, and we are treating all the values of equal importance, and we are just filtering the original image and compute scalar products. By computing the scalar products and considering that the filter has some weights that are pretty much 1 divided by the total number of pixels that are considered, then we are in the case of an average filter. So if we are looking at this image after applying a box averaging, so okay, we are not getting any sort of pixel-wise spikes or noise readings. However, the direct result of averaging is that we are ending up with a blurred output because we are combining pixel values in local neighborhoods. Okay. So a solution to this is to apply some iterative functions or some odd filters and so on. I'm not entering neither in this part. What is important? Okay, so what is important here is that are quite a number of ways of filtering, and many of these filters are defined for some assumptions. So what is the main and the most critical part is to figure out what is the kind of corruption we are applying to. If we know that is a Gaussian noise, or if it's some salt and pepper noise or whatever other kind of noise, already we know quite a bit, and we know to adapt and to pick up some solutions that are also known to work or to handle that kind of corruption. So, for example, here, if we are looking at median filters, so what happens in a median filter? We are looking in a local neighborhood and order the intensities or the values in the local neighborhood. For example, rank them from the smallest to the highest, and then we are just picking the middle value. So in this way, we are just picking a value that is already in the image. We are not creating new values, okay? And moreover, we are just betting on the fact that the image still contains most of the original information. So for example, here is a simple example that given some input image or some input sequence with some a lot of 1s and 1, 7, okay? If we are applying a simple median filter, or then the odd value will just go out. So if we have a salt and pepper or some noise that is just provides extreme value or a low value or something that is uncontrolled in the image from time to time in the pixels, okay, then obviously it's better to apply like a median filter, because we'll just replace the odd values with something that is commonly found in the local neighborhood. Okay, so here are some simple median filters, and mean filter for some input. So if we are seeing at this input and the values, the median filter will just remove the outlier, this outlier here, that is a local outlier, while the mean will pretty much change everything and blur the things. So that's why if we know that the noise is just something that is appearing once in a while and is just disrupting, is an outlier in the signal, then probably is, the better idea is to take directly the median. At least we are not changing much of the information. If we are applying a mean, pretty much we are applying a blurring step and adjust or modify most of the values in the image. Okay, so the median filters, the median completely discards the spike. Linear filter always responds to all aspects. Median filter preserves the discontinuities, like here, while the linear filter, the mean, produces rounding off effects. We have seen here that is just rounding these values. So, for example, if we are taking this image and we are applying a median filter, we are sharpening some edges, destroy, but at the same time, destroy some edges and protrusions. So if we are taking the median filter and compare with a Gaussian filter, so in the case of a Gaussian filter, we are just getting a higher emphasis on the middle value in a filter that has 2D support, is let's say 3x3 or 5x5 support. Okay, so the middle value will be more emphasized. This means that we are still relying quite a bit on the original values in the image. Then we are getting something that looks more smooth, closer to the average filter, but at the same time, we are not getting something that is quite unnatural. So here, somehow, because of the sharpening, we are ending up also destroying some natural feeling of the eye or lips. Okay, so it's not like a simple answer. So we are looking again, we are getting some input, and this input has some noise. If we are applying median filter a number of times, we are just ending up with something like this. So we are over smoothing in some areas and gets quite patchy. Okay, so I did not discuss too much some noises here, but I invite you also to check them: exponential noise, real light noise, okay, and see exactly what is about. Anisotropic diffusion principle. Okay, I will just skip this part. And if we are looking at some simple example, we have some noisy input image. The ideal image, if we have access to the ground truth, and here are some examples. If we are applying this kind of diffusion approach, the more we are going and optimize, the more we are smoothing out, but also removing quite a bit of noise. So in an isotropic case, we are able to get closer to the ideal image without the, but also we are not reducing all the noise. Okay, anyway, so I'm just skipping this part. When it's coming to the blur, yeah, there are quite a number of ways of doing, but here, again, I'm just skipping, partly because most of those are using the Fourier transform and the inverse filtering and Wiener filtering. Okay. So Okay, when it's coming to the contrast enhancement, so in order to solve the bad contrast, we can just compensate under or overexposure, and we can also spread out the intensity range such that to cover better the interesting parts of the image. So if we are looking at those two images, and again, we are looking at some histograms, so we have the values between 0 and 255, and here is pretty much is telling us something about the frequency of these values, pixel values. Okay, then we know that for this case, we are getting some values in the 0, some values in close to black, so full saturation or no value. And here we have some example of bad contrast. So this is a good contrast, this is a bad contrast. And now if we are just looking at those two, we are just seeing here two curves. One is with corresponding to that and one to that. Okay, I will not keep you waiting. So the one that here shows almost 0 and has a sudden change from 0 to something that goes to close to 250 something. Okay, this corresponds to that, a bad contrast, while the other one that gives a better spread, the blue curve, corresponds to the first one. And if we are looking at histogram, it's quite clear because we have a good spread, we are getting a good understanding and visualization of the information. And if we are looking at the cumulative histogram, this means if we are adding out the occurrence of the pixels up to some value level, okay, we just see that the upper image has something that is more ideal. So this means that we have a spread and a good uniform distribution of the values and the pixels in the image. Okay, so in order to change these histograms and in consequence to improve the contrast, okay, we can just do a very simple mappings like monotonic mappings. And here are some examples. If we are just taking the original or the old image, and we are just lifting everything with some gamma coefficient. And here are some different gamma coefficients applied, and the result in the output level. Okay, so this is like a simple visualization. So if we are doing this operation, then basically we are just mapping the old intensity to some new intensity, and in consequence we are altering the histogram and the way it's looking, the cumulative histogram. And yeah, we may also benefit and get better contrast. So this is the original image. Applying this gamma or this gamma, we are getting different visual outputs. Okay, so this is if we are doing like a manual operation, but we can do a histogram equalization. The final and the target is to have like a flat histogram. This means all the values will have an equal number of pixels in the image. And the cumulative histogram is just going like a diagonal, so it's a very well behaved curve. Okay, so here is our result, original image into the histogram equalization. And we see after histogram equalization that we are getting a sharper and higher contrast, and yeah, generally is easier to read and to see what is there. Okay, this is another example. If we are just taking the bad contrast, and we are applying histogram equalization, we are ending up with something. Okay, so the histogram equalization in the end is still aiming at mapping a set of values, so intensity values or levels, okay, from some pixels to another set of values, such that in the new set of values, we are getting to the aim of having something closer to a flat histogram, and and also having some cumulative intensity probability that it gets closer to the diagonal behavior. Okay. So this is just some simple visualization. If we have our original histogram of the values, something like this, okay, then obviously we just want somehow to adjust and move some of the pixels and values more to the left, such that to cover this area between 0 and 100, or what is here, okay, and to reduce the here the overall number of pixels in this range, and also to spread and to get something more on the end range of levels values. Okay, so I'm not going to take here step by step what happens in the histogram equalization. You could do that yourselves and see exactly the result. Well, the histogram equalization is also implemented in PyTorch and MATLAB and most of the tools. And here you can just see something like the original and the flat histogram. So you can see that the values were spreaded, or the distribution of them, the density of them were spreaded, such that we are getting a better contrast in the original image. Okay, so this was about the histogram, and this concludes today's lectures. I don't know, you have some questions? So the slides from this lecture will be placed on the webpage, and I will place also on the webpage the home assignment. You'll have like 3 weeks to provide some solutions to the home assignments. The home assignments are designed and defined in a similar manner like the topics that you'll have in the exam. So will just be 8 exercises or simple questions or problems that you need to answer, and are related to the material that already was covered, and could be also some questions that might require a little bit of exploration. But yeah, the purpose of these home assignments is on one side to help you to get acquainted with what will be in the final exam, and on the other side to move part of your learning to the semester. During the semester, it's better to check a little bit the lectures and the material that is coming with this course, and to be prepared from during the semester and not learning in the last moment. Okay, so this is about, yeah. If you have questions, just let me know. If not, okay, I will just ask you to stay a bit more, just to make some presence. I will just Okay, so if nothing else, then see you next time. And don't forget, you'll have the laboratory with Florin Vaslianu. And in the laboratory, you'll go through topics that are covered in the lectures. And probably you may end up moving a little bit ahead with the laboratory starting from the third or fourth week. Okay, so if nothing else, then thank you for attending and see you next time. Have a nice weekend.
Thank you. Have a nice weekend. Bye-bye.
Bye-bye.
Thank you. Thank you. Bye-bye.
Thank you. Have a great weekend. Bye.
Thank you.
Very much.